Hey, what's going on, everybody? Welcome back to the stream. I'm excited for another fun day of hanging out with you all. It's definitely been an interesting couple of weeks here working on projects and such. Sorry, I'm still getting a couple things set up, but yeah. So, as the stream title implies, I have been writing a lot of Rust, and that's been a lot of fun. It's been very challenging, but it's been a lot of fun as well. I'm forgetting my keyboard shortcuts here. How do I adjust the size of my windows? Interesting. So I got my splits, and then thought this was right. Shift Alt. Okay. Yeah, so I've been programming a lot on my laptop, and the keyboard shortcuts are slightly different on my desktop. Let's see here. Yeah. So welcome. I'm just gonna start some music for me really quick. I can't share with you all, of course, because of DMCA, but of course, feel free to listen to whatever sounds good to y'all. Hang on one sec. Just got blasted. Okay, there we go. Scared me a little bit. Right. So, yeah, I've been working on a project here for a couple of weeks. So I've been telling myself for a long time that something I really wanted to do was do a bigger application in Rust. I have been following Rust for the past 7 or 8 years, really. I tried to use it right around 1.0, did a couple of kind of small projects, and I've done a couple of smaller libraries here and there. And actually, a couple of years ago, I've talked about this on stream a few times before, but I actually did. So if you go to interpreterbook.com, I completed this book. This is called Writing an Interpreter in Go by Thorsten Ball. This is a great book, by the way. If you are interested in programming languages or the ability to, perhaps understand how things kind of fit together, this book is excellent. And actually, there's also a sequel as well called Writing a Compiler in Go. So a couple of years ago now, I actually did both of these projects in Rust, and that was a lot of fun. So basically reading the concepts, trying to understand how they all fit together, and then instead of taking the Go code literally and writing it out, I tried to create what is effectively the Rust equivalent. And I had a lot of success with that, but something that, of course, for those of you who've known me for a little while, I love doing networking problems. So historically, a lot of what I have done has been in the networking and system call type space. And I know in Rust for a long time, there was a lot of work being done around asynchronous I/O with things like Tokio, futures, etc. So that's where this project comes from, actually. So we are at the point now where I have implemented a network block device client and server, at least the beginnings of a client, but the server works and actually can perform reads and writes using asynchronous Rust with futures and the Tokio runtime. So Tokio is a really interesting project. Basically, it lets you kind of write your Rust code in a way where you don't have to necessarily care about managing the concurrency and such. Like the Tokio runtime kind of handles that for you. And it actually implements a work stealing scheduler of sorts similar to what we do in Go. So it's pretty interesting, actually, because, those of us who've written Go for a long time are familiar with kind of how Go abstracts all those concepts away from you. In Rust, Tokio and the futures ecosystem, async I/O in general, seems to be kind of the new hotness, and it's stabilized quite a bit. So it's been a lot of fun, and I figured that it would be a great opportunity for me to learn some Rust by kind of putting everything together and doing a network protocol implementation in asynchronous Rust with Tokio and futures. So I've done a lot of control plane type protocols in the past, things like the neighbor discovery protocol for IPv6 or, different types of sockets and stuff. So I kind of wanted to do something that was more data plane. And I figured for that, you probably want something that's like a storage, like a file transfer protocol. Oh, here we go. I'm a Twitch noob. Will this be available to view on demand later? Yes, it should be. As far as the VODs go, they are available online, at least for a couple of weeks on Twitch. So if you go to my page after the fact, they will be available online. I have historically uploaded things to YouTube as well, but frankly, I've been kind of lazy with that recently because I have to do some editing, which kind of stinks, and wait for YouTube to upload and process, which kind of stinks. So typically, I haven't been uploading the past few streams, although if there's interest, perhaps I can do that. And honestly, I guess I could just leave an uncut stream and allow the viewer to scroll through themselves. Maybe that's not the worst thing. But yes, this will be available for at least a couple of weeks, and of course, the source code is all online. So the repo we are looking at today, !project in the chat. And actually, I've got it up right here as well. So this is my nbd-rs library. This is my implementation of the network block device protocol in Rust. So yeah, this is pretty cool. James, thank you for the bit. You're assuring your lead. Thank you for the 1 penny. I appreciate that, my friend. So this is kind of an interesting protocol. The way that this works in the Linux kernel, at least, is the negotiation to initiate storage happens in user space. So the network block device client reaches out to the server and figures out what sorts of parameters the server supports, what types of commands, perhaps gives hints about what kind of storage is actually backing the device for things like SSD trim functionality and etc. And once the negotiation's actually done, you take the socket file descriptor and either use netlink or an ioctl, and you hand off the file descriptor to the kernel, and then the kernel does all the data transmission for you. So I suppose one way we could do this, actually, let's go back. So I've got the code open here. I guess for the time being, let's go full screen terminals because we're going to just kind of demonstrate how the project works before we get into it. So let's see, control. It's kind of funny because, like I said, I don't really remember how to. It's been a while since I've done this on my computer. Control Shift B %. No, I forget how to make a vertical split. Control B pipe. I forgot. I actually forgot how to make a horizontal split. Oops. Anyway, it doesn't really matter. So what we're going to do... Oops, I forgot my tmux key bindings. I am going to run the server side of this. So now we have a network block device server running. It is bound to the local port and such. If I go into my machine here, we'll just scroll this up a little bit. And actually, I have a test command, which is pretty useful. So if I go back to my code briefly... I'm going to close the pre-flight now. No longer need that. Control B %. Yeah, I think you're right, Jared Bauer. Control B %. The problem is I have things bound slightly different on my Kinesis. Control B C is next. Yeah. So Control B Shift %. Yes, you're right. Thank you. Oh my gosh. I feel really silly now, but yeah. So okay. Control B %. Yeah, thanks. I appreciate that. It's been a while. Yeah, so we have things running now. We've got the server running, and actually I'm going to pull up a command I have written down in the client server. Here we go. So basically, we need to load the kernel module for NBD. We initiate the NBD client, in this case on localhost because the server is bound to localhost, and we're just going to run DD, like basically just copying the bytes as fast as we can, and then disconnect all the devices. So this is just kind of a proof of concept. So if I run this, it'll take not that long. So you can see here on the left that the client has actually negotiated a connection here. The client is telling us that it supports the fixed new style negotiation as well as the no zeros flag. It's requesting basically to access the default export. The server is responding, okay, you can take that export. Here's the information about it, such as its name, its description, the size, which is a 4 GB file. Prefix space will scroll through different default layouts too. Really? So Control B space, no next window. Oh, okay, yeah, because I have. Oh, I actually didn't know that. I've always done N and P for next and previous, but good to know. One of the really funny things about streaming on Twitch is that people will tell you, like, why are you doing it this way? Like, there's a way easier way. And for example, it took me a long time to discover that Control L clears the terminal instead of typing clear. Much easier. So I appreciate all of your help. Yeah, so as you can see here, actually, we were able to use DD. We copied the entire contents of the network block device, which is being managed by the kernel on the client side, to dev null. We disconnected all the devices, and we got a transfer rate in cargo release mode of 908 megabytes per second. So we're pushing like 10 gig speeds here pretty much without basically any optimization on my part. Like I'm not I'm not really great at benchmarking IO type of loads and such, but I'm pretty excited about this. So actually, if we run this without release, you can actually see a small difference. So I'll run this back in debug mode really quick. We'll repeat the same command. And it should be just a little slower. 882. Yeah, so it seems like the release mode doesn't seem to make a massive difference, but it is still interesting. So what's cool about this, of course, is that since we have the block device available, we can, first of all, connect to it. we now have dev nbd-0 available, so I could actually make a file system on this. We've already got a file system, but I can make one. I can mount the device, dev nbd-0, mount nbd. We can actually get into it. We can do whatever we want, right? We can copy files and such, perform file IO. So I guess, for example, do I have anything that's like, I don't know. Let's go ahead and allocate a file on this. So what, like a one gigabyte file or something like that. File.bin. Shoot. Okay, so we've allocated what appears to be, I think fallocate does some tricks to make like an empty sort of file, but you can see now that the space is reserved. So we've used 1.1 gigs out of this. And I guess for other demonstration, so readme text hello world. Okay, we're going to go ahead and unmount this now. We are going to basically disconnect all of the network block devices. So I have this loop in particular because there were times where I would hang this and it had to basically disconnect all of them in a loop. So we have now unmounted the device. We can stop the server. And actually, if we choose to mount the disk here, disk.image to the temporary, just the temporary mount point, we can see for example, that like our files are on here. We have the README. So yeah, this works. We actually have working network block device IO. This is pretty cool. So of course, this is just working over the same machine. I did test it last night on my laptop over Wi-Fi. It was really slow. I think my Ubiquiti APs are probably a little dated at this point and such. But yeah, it does work. So that's pretty cool. So how does this all fit together? I guess that's kind of why we're here, right? Is to talk about all that. So let's go back to the code. So I have packaged this up just a little bit. I suppose maybe it would help first if we look at the docs. So doc open, we are not, there we go. Hang on one sec. So we're building the docs. It popped up in the wrong browser. One sec, page down, there we go. Yes, so if we run cargo doc -- open, it will actually show us the docs for our current crate. So I'm calling this crate MBL or MDL NBD because there's already a couple of NBD crates and such that seem to be various levels of complete. Yeah, so I guess kind of this crate right now exposes both high and low level interfaces kind of through the same API. The highest level types are the client and server, and then there are varying levels of like low level types in here as well. So if we go to the client, for example, zoom in again. A client, the way you use this is you either perform a handshake on a stream that's already open. The stream has to be something that implements the async read, async write, and unpin traits. For those who aren't familiar with Rust, basically like these are traits that the Tokyo network or Tokyo IO libraries provide. And Tokyo, for example, has an asynchronous version of the TCP stream. So something you would typically do here is like a TCP connection. However, you can run NBD actually over any sort of like, stream-based transport. So it could be TCP, could be Unix socket, could be something like vsock, I think would be pretty interesting as well. So I actually have a helper here that if you specify this connect function and anything that it's a 2 socket adders, which could be like a string or whatever else, we can actually establish a TCP connection on demand with the address and then perform the client handshake. So once you have this client type, there are a couple different methods you can invoke on that. So far you can do info, which performs an info request to get the export metadata. And then there's go, which does the same thing, but this will also eventually allow us to start data transmission. So that's something I'd like to keep working on. We're not there quite yet. More fun employment projects. Yeah, so I really wanted to do a big Rust project, and I've done exactly that. And it's been a lot of fun. And I would have liked to stream a lot more of this, but kind of the situation I ran into is we had the holidays, and then as soon as I got back from the holidays, I was sick. I was sick with not COVID. 8 or 9 days of not feeling very good and also not being very good at Rust. So I wanted to work on this on my own. Excuse me one sec. So I got to the point where I'd been working on this for about a week or something, started feeling better, and it's like, well, shoot, I've already done so much off stream, so at what point do I start showing it? But I think that, today, for example, would be a good day. So I'm excited to share what I've learned so far. So again, this client type is not done quite yet. Basically, this go function should produce an IO connection here. It does not quite yet. The other high level type is this server. So conversely, this has a bind function, which will bind a TCP listener on whatever address you specify, typically any address port 10809, so 10809. And then once you have that server, we basically create a future here, this run future. So you pass in this device's structure that coordinates the type of device you're serving. And the block device here can be anything that implements read, write, seek, and send. So it needs to be able to be sent across different threads. It has to have a static lifetime, which means that it could exist possibly for the rest of the program. And it has to implement read, write, and seek. So for example, things like files implement this, in-memory buffers, possibly other network streams, maybe not seek. But yeah, pretty cool. So I've got this working with files and in-memory so far. The lower level types we can kind of get into, but I guess at this point I'd rather just show some code. So if we go back to, there we go. Client side of things, we connect to the server bound to localhost. We perform the handshake and get the default export. So easy enough. So if I go ahead and start this really quick, let's run the server, cargo run bin client. What's it called? Isn't it called nbd client, I think? Yeah. Yeah, so you can see here, we have the server running, and the server has sent an info reply here. The client chose to request information about the export, the name, the description, and the block size. Hey, Taryn, welcome back. Thank you so much for the sub. Welcome back for 20 months. Holy shit, that's pretty cool. Thanks, man, I appreciate it. So as you can see here, the server returned all of the requested export information, and the client was able to fetch this and see it. So this is effectively what the nbd client that I was running earlier is doing. It's just this is my version written in Rust. Sorry for the delay. You were making coffee, missed my going live. Yeah, no worries. I mean, we're just chilling. We've got a lot of stuff to talk about, So speaking of coffee, so I got this pretty cool. Here we go. I got this mug called an Ember mug. This is a Christmas gift. And this thing's pretty cool because it actually has like a little battery built into the bottom and it heats the coffee. So I went and bought coffee a little bit ago, came home and I've been drinking it kind of slowly. So I put it in this mug and turned it on and it's working pretty well. So would recommend so far, at least for the couple of weeks I've had it. It's been a cool gift. So the client here, again, this is abstracting over a lot of different concepts. We'll dig into this, but then the server, similarly simple, I suppose. So the server here, you were jealous of that Go Space Shuttle poster? Oh, yeah, over there. So that is over there in the corner, that is like the Go 10-year poster, I believe, something like that. Got my chair there too. Let's hide that. There we go. Yeah, that was given out, I think, for like Go's 10-year anniversary. I think I might actually have some extras. I could possibly mail you one. Remind me after the stream, and I could probably try and send you one. I think I might have like 2 or 3. Not to bring up Go during your Rust programming. Hey, it's fun to do both, I've been interested in Rust for like a long time. Of course, I'm a well-known, I would say I'm a somewhat well-known Go community member, I suppose, but it's fun to do different things too. So getting back to this, basically the server, you bind it to an address and then you run it. And when you run it, you pass in the devices you want to serve IO for. So this devices structure, you give it an export, which is effectively the metadata. So the name of the export, description, the size, block size, etc., whether or not it's read-only. And then what I've chosen to do here, so I guess this is something where I've tried a lot of different approaches and I wasn't sure what worked. But effectively what I'm doing is I'm passing a function here that opens up a handle to a device. So once the client successfully negotiates data transmission here, this function is invoked. It will actually open up this file called disk.image for reads and writes and then return it. And then this device is used as the backing device for the nbd server. But this is generic over any type D, where D is read, write, and seek. So it could be not just a file, but also, for example, like an in-memory buffer or similar. So this is something that I had to play around with a lot to try to kind of figure out how everything fit together. And it's something that I'm not sure how idiomatic it is, but it does seem to work. So I guess now that we've talked a lot about the high level type of stuff, does anybody have any questions, things we'd like to see specifically, or should I just kind of dive into what we've done so far? Yeah, so kind of the way this works, let's take a look at the server. I think that's where things get kind of interesting. So the server type here manages, again, our list of exports, which are basically the metadata for the devices we send during Handshake, and then the hash map of device names to these device function handles. A device function is a boxed function that returns a result of D, where D is read, write, and seek, and it also has to be send and sync, so we can send it across thread boundaries. So yeah, this took me a little while to get right. But I'm pretty happy with the way it came out. So to construct devices, you call this device's new constructor, you pass an export, you pass the function to open the device, and you can also add additional non-default exports. So NBD has this concept of a default export, but a server can have as many exports as you want. So say, for example, here I run the server again. NBD, oh shoot, address already in use. Interesting. I guess we got like a transient port reuse thing. So if I run nbd client-l, we can actually see here we list the exports on the server. So in this case, md layer nbd-rs, this description string. But I can actually choose to export, one or more exports here. So if I choose to add more, they will show up here as well. And then the client can request them specifically by name. So for example, if I were to run -n, I believe, queries an export by name test, the server will say the export is not found test. So that's how you actually activate different exports. So this can serve multiple devices at once. So our server type here, perhaps missing SO reuse port. Yeah, I think so. So, I'm always a little hesitant to set that. Like, I feel like it might be papering over some other issue, but I guess the thing is that like I had already quit the program and tried to run it again, and the port wasn't ready. So I don't know if that's just like the Linux bookkeeping not being done yet. But yes, probably something I should investigate. So for the server here, we create one by calling this bind function. T is 2 socket adders. So we create a TCP listener, we wait for it to be ready, and then we return this handle to the server, which has the listener inside. When we call this run function, basically we start passing, for example, the list of devices as well as a set of locks. So this server has the concept of being able to lock a device. So for example, if you have a blocked device that's exposed, SO reuse port is an ancient and dangerous incantation. What's up, Peter? Good to see you. Yeah, that's been kind of my experience as well. Like, I feel like it's one of those things where I don't want to use it unless I'm absolutely sure of what I'm doing. So I'm tempted just to not mess with it right now, This server has the concept of locking devices. So basically, whenever a device is open for transmission, the client acquires a lock on it so that any future device or any future client that tries to connect to that device will be turned away, essentially. And I guess there are cases where you can actually have multiple connections to the same export, but the server has to handle that very explicitly, and I'm not there yet. So right now I maintain a list of locks, which is just a hash set, mutex, arc. Every time you send it across a boundary, a thread boundary, you create a new reference, you acquire the mutex, check if it's in there. We'll go through that. We accept TCP connections, and here, the protocol actually recommends setting no delay. I understand this makes things potentially perform a little better. It would be interesting to try that little synthetic benchmark I just had just now with the difference without running this in either of the sockets, but for every socket we accept in this server type, which is a high-level type, it will do this for us. And then we actually call Tokio spawn. So this creates a new task essentially in the Tokio runtime. And for every accepted connection, we spawn it into a new task and we go back to listing for more connections. Once we have actually moved the socket and such, like everything into this block, we create a server connection over the TCP stream and then we begin processing. So the processing is effectively, I'll just open this up just a little bit. Some of these lines are a little longer. Yeah, so basically what we do here is we initiate the connection handshake with the list of exports we were passed in when we started up and the list of locks as well. So the client will basically, by telling us which options it wants to send, it could either request data. So for example, that list call I just showed you doesn't actually start data transmission, but the go call will. So if they send a list or info, for example, it will essentially return none. We are done. We basically drop the socket, clean everything up, and we're good to go. However, if the client chose to begin transmission and they requested a valid export, we actually return this server IO connection here. We insert a lock for the connection because we don't want anybody else to use this. And then we actually fetch the appropriate device, which will never fail because by this point we've already checked that the device name is valid because it was passed to the server type or the handshake. So the server chose a valid export, which is or the client chose a valid export, which is returned here. We fetch a handle to it, open it up immediately, and then begin transmitting on it. This will block, and then once this completes, we drop the lock for that export, and we return. Yeah, so there's a fair amount going on here, but this is pretty cool. One thing I wanted to point out really quick, so from the last time I did Rust to now, I understand that Rust Analyzer is the new language server for Rust. I used to use RLS, but now it's Rust Analyzer. And it does this cool type annotations thing. So for example, here you can see that con is a server IO connection over a TCP stream. This is very, very useful to the point where I will sometimes like separate lines out just so I can see, for example, the intermediate type of something. So Rust Analyzer is awesome. Definitely recommend checking that out. As far as the lower level mechanics, so now we're getting into kind of the weeds here. So this is the high level server type. Like this abstracts away a lot of the stuff you don't necessarily want to care about. But say, for example, you already have a TCP listener or Unix socket listener, vsocket listener, etc., and you want to kind of implement some of this logic on your own. I actually have this server connection type as well. Server connection is generic over S. Hey, what's up, Super Shabam? Wave just dropping by for a moment. Hey, good to see you here. Hope you're doing well, man. So again, this is generic over S, where S is async read, async write, and unpin. So effectively a Tokio TCP stream, Tokio Unix socket, etc. And then we have this raw connection type, and this manages kind of the low-level I/O buffering and reading and writing of things. We'll dive into that in a little bit. As far as the handshake process itself, so this is kind of where we're getting into the weeds of the NBD protocol. The first thing we do whenever somebody opens up a connection to us is we, as the server, we immediately send a server handshake with the flags that we support. So in this case, I guess NBD has had 3 different iterations of handshake over time. There was what's called old style, new style, and then fixed new style. So we only support the fixed new style because it is the current thing. I guess this protocol has a fair amount of legacy over time and such. And this no zeros flag, which stops basically an unnecessary big block of zeros from being written. So we write a single frame to the connection here. Frames are kind of a Tokio concept of sorts. Excuse me one sec. Basically, we are chunking this protocol up into these frames, which we send back and forth with the client and server, so we can negotiate things in kind of a more convenient way. We'll get into this, of course, as well. Once we send the opening handshake, the client can begin sending us messages. Basically, for every time the client sends another set of options, we'll handle those, process them, and ultimately either return because the client chose not to begin transmission, which means that, for example, the client chose not to return a frame, so we hang up. Or, for example, if the client forcibly disconnected while we were waiting for them to send a connection, we also don't really care. It's not really our problem at that point. So the client will send us their client options. If we read a frame and it matches that type, which is the client options frame, we begin processing those options. So we expect the client flags, for example, to match the same set of flags we are advertising, which is the fixed new style handshake and the no zeros flag. And then we begin basically producing responses to all of those requests. So something that still, as a Go person, kind of weirds me out sometimes is the use of like iterators in Rust. So for me, I had originally written this as, effectively a for loop, but instead now we have, we iterate over our client options, which is a vector of option requests. We consume the iterator. We map everything, so each option request gets turned into its equivalent response by associating data from the request, the exports, and the set of locked data. And then we collect this all back into a vector of option responses. So, it works. It's definitely the kind of thing where it takes me some getting used to. But the thing is that when I'm writing Rust, I'm trying to write Rust like a Rust person would, instead of writing like a Go person would. So I guess what's nice here is like you don't have to like necessarily care about the capacity of the thing or how many loop iterations you're doing, because the iterator, for example, or the collect function just kind of takes care of that for you. What's up, Clays? Yeah, it is fancy. It's pretty cool though. So something the client can choose to do, if the client, for example, is sending us multiple messages, it can choose to abort the request at any time. If we got an abort anywhere, then we drop everything else we're doing. We don't begin data transmission. We send no metadata. We just write that, okay, we got your abort and we're doing that now, and we're going to drop the connection, and that's it. Otherwise, we tell the client, for example, if it sends us some kind of option we don't recognize, we tell it that, we don't recognize this particular option code, but we're going to proceed anyway. So the client can choose at that point to figure out how it wants to handle things. Your limited experience is that functional iterator style Rust gets you into type trouble TM real fast. Yes, that is true. So for example here, I can actually demonstrate something that's kind of like a gotcha. It took me a little bit to figure out. If I get rid of the type for this, I'm pretty sure this will start complaining that it can't figure out the proper type. Let's see. Yeah, so for example here, like this is just some kind of iterator of unknown things, and we actually have to explain to Rust like what it is that we want here. So vector of option response gives you that. It's super slick when it works and super time wasty when it doesn't. Yes, absolutely. I'll eventually get to the point where I'll show some of the stuff I've had to do on the IO side as far as generics go. And when you get into multiple like generic bounds and lifetimes and everything all together, you definitely get some type soup, but it's starting to make sense to me too. I think I really just needed to kind of like nail it down and figure out how it works. Here's another sort of like Rust iterator thing. Essentially, we want to fetch the first option from the iterator here, and the first option, hang on. Yeah. So we iterate over. You would love to read my how to async plus iter tutorial. So basically what I did when I was writing all of this is I just followed the Tokyo tutorial. They have like a mini Redis is what they call it. I went through effectively this entire thing, and there are still parts I haven't really gotten to. So for example, like Tokyo has a select macro, which is very much like our go select we're used to. So there's a few things in here. It has channels as well. There's a few things in here I still haven't really gotten to, but this tutorial was quite helpful. So I kind of went through this and tried to understand how it worked. And then I actually pulled open the source code of this mini Redis crate and used it as an example to basically create my own. So I guess I'm under the assumption here. Tokyo docs have improved a bunch since I last used it. I should probably give it another shot. Yeah, I'm pretty happy with it overall. How coupled to the Tokyo executor and runtime is that stuff? See, I think not necessarily. So for example here, I guess in my particular case, I'm using these async read, async write types, which are part of the Tokyo IO libraries. But otherwise, like for example here, pub async function handshake, like this just produces a future, and I think you could execute this on any runtime. I think even not Tokyo. Like I understand there's a couple of competing ones. I chose Tokyo because it is the one I have heard the most about, and it's the one that seems to be popping up most frequently in the community. But I think that, for example, my high-level server type is using, my high-level server type is using Tokyo spawn directly, but my low-level server connection type is not. So I think aside from the async read, async write traits here I'm using, in theory, this should be portable to different runtimes, but don't quote me on that because frankly, I'm not a Rust expert. Hopefully there's somebody in the channel right now who can perhaps share some knowledge, but I think in the meantime that tying my code to Tokyo seems okay. I'm also using Tokyos, for example, like the network stream types, the Tokyo TCP stream, and etc. I do not know how it would work if you use the standard library types. I suspect they are probably all blocking primitives and it would be different, but the Tokyo versions are based on a library called Mio, which is kind of like a low-level async epoll back to library, kind of similar to like Go's runtime network polar, actually. Should be portable to other runtimes, MD layer. Yep, exactly. What's up, Ray? Yeah, so I guess kind of getting back to this. So basically what we do here is we need to figure out if we're going to transmit or not. So the way that we can initiate transmit with nbd is by having a go request. And when we get a go response here that's valid, as in has returned a chosen export, we clone this out. We respond to the known options. So for example, things like the go, list, abort, etc. And then depending on whether or not we are transmitting, so we match on maybe transmit, we either return some server IO connection, which means a connection that's ready for IO with this export, or we continue and keep waiting for more client data. In the other streams I participate in, I would have totally added that to the quote bot. There should be a quote bot in here. That'd be pretty funny. Can Nightbot do that, or is there something different? That would be cool. Yeah, so at this point we've negotiated an IO connection. This is where things get a little more interesting for sure as we get into the IO stuff specifically. So kind of what I tried to do with this library is have different types that I have different types here that kind of indicate what the type is capable of doing at any given time. So for example, a server connection is capable of calling handshake, but you can't call transmit on a server connection. You have to call handshake and get a server IO connection. At this point, the server IO connection takes basically ownership of the underlying stream. And then you can choose to transmit on this. So I've basically tried to make it hard to misuse this by having different types that effectively pass things along. So for example, here the IO connection will actually take ownership of the underlying stream, the network buffer, and this read-only value. And when we call transmit, we also take ownership of the device here as well. So device D, which implements read, write, and seek. Notably, so the server network stream here is asynchronous. So async read, async write. The device uses synchronous reads, synchronous writes, and synchronous seek. So I guess I don't really feel like it would make sense for me to have those be asynchronous. So I chose to use the standard library traits here. Hey, what's up, JV Pratt? Good to see you. So we'll talk about transmission shortly, but as far as I mentioned earlier, like generics, type soup sort of stuff, this is pretty tricky. So I have a device type here, which is generic over a couple of things. And basically we take this read, write, seek, and if the device is read only, we erase the ability to write from the type. So we pass the read in here. So if the device is this variant, which is read, it no longer has access to the write methods whatsoever. So we're actually using the type system to kind of enforce that invariant, which is pretty cool. In the future, there could be things like, for example, SSD support in here. So if we wanted to like send trim or something, we'll probably have another variant, but it's not there quite yet. Good to see you back on streaming. You probably missed a stream or two. Hope you're well. Yeah, I'm doing really well. Yeah, I was gone for holidays for a little bit, and then I was sick for about a week, week and a half. I started working on this project. I wanted to kind of make some progress and frankly not be a total noob at Rust on the stream. But I've made a ton of progress the past couple of weeks, and I really just wanted to share what I had learned. So I figured that if nothing else, I would go through and talk about everything I've learned so far and probably do a little bit of development as well. One sec, I'm gonna grab some more water and then I'm gonna sit down. I think it's about time. Yeah, BRB. One sec. All right, we're back. Yeah, so something I wanted to mention, I guess, for those who haven't really seen async Rust before, you may have noticed this await call all over the place, like async await. My understanding is basically async and await are syntactic sugar for things that implement the future trait. So the way the future trait works basically is you have a type, you're able to pull whether or not it's ready, and then once it is ready, it returns an output, which is, for example, like, could be a network stream, could be an IO result, could be basically anything. So I want to show, for example, like kind of how that works. So if we go to the connection tests really quick. So this is interesting. I have a couple of tests here basically that test, what are effectively the interactions between the client and server. So if I run cargo test really quick, we will see all the tests passed so far, which is good, makes me happy. For the listener here, first we are going to bind a TCP listener. We're going to call await. So basically we need this future to complete right now because we actually need access to this TCP listener. On the client side here, we call client connect, the listener's address, and expect, but we don't call await. So instead of returning the client, this returns impl future output equals result of client TCP stream box error, kind of type soup again. But basically, now that I have this client handle, I pass these to two different Tokyo tasks here. So we have the server running. The server will actually accept a single connection and process it. And then the client, I put the client into this new task here. We invoke await on it, and then this actually gives us the output client. So that's kind of the key here, is that when you run something or when you create a future here, you don't necessarily have to await it right away. So I'm able to, for example, create the client and bind it to the server's address, but I don't actually bother completing that connection or waiting for that connection to complete, rather, until here. So in the background, essentially, this will start running. This will actually begin the TCP connection, but I don't need that connection up until this point, so I'm able to continue execution elsewhere. So that's pretty cool. So this test actually verifies, again, that given a list of exports, the server is able to serve data for those exports. The client's able to request info. It's able to get the default export and verify that one existed. It asserts that the export is actually present. And then we wait for both the client and server to terminate. So in Go parlance, this is kind of like having a couple of Go routines and a wait group here. And we can actually wait for things to stop together. So pretty cool. Pretty cool. I've learned a lot with this. It's like one of those things where, oops, don't want that. Sorry, I just lost my chat room. That's weird. Yeah, I feel like I've really learned a lot about all of this, and this has been a really interesting and fun experience, like writing all of this. Certainly the type soup thing that Peter alluded to earlier has been difficult, but otherwise, this has been a lot of fun. Twitch chat has been crashing for users a bunch over the past few days. That's a bummer. I suppose I'd like to show at least a little bit about like kind of the low-level protocol bits. Certainly the handshake stuff is all pretty complicated as far as negotiating options. So I think probably what I will do is I will show the transmit connection instead, because it's actually comparatively simple. The basic idea, and when I was copying the Tokyo docs, for example, you end up with this frame enum, and basically this frame enum can represent all the different possible operations. So for example here, a client can disconnect, we can return an error to the client can issue a read, and we can respond to that read with the number of bytes that we read. The client can issue a flush, or the client can issue a write. And the way we actually implement the frame is we have a couple of different methods here. So we have check and we have parse. So if I go to the connection type, once we have this raw IO connection, I promise I'll explain the trait bounds and such. This is a thing, TM. We begin serving requests continuously. We keep awaiting the next IO request, and as long as the IO requests keep coming and we have a valid one, we keep processing them. If we return none here, actually, that means we do not have enough data in the stream. At that point, we need to read more into the stream buffer and basically determine whether or not the client hung up, or otherwise keep processing IOs. So for every IO, we take a cursor over the current buffer of bytes that we've read. We begin checking the frame. The frame check function will tell us basically either, yes, we have enough bytes for a valid frame and we can process it, or no, the frame is currently incomplete. So say, for example, like you expect 8 bytes, but you've only read 6. It will actually return, I have helpers here, this will return this incomplete, which returns okay, none, which means that the operation succeeded, but we could not read a valid frame, which will cause us to read more bytes and then try again. Once we have an entire frame, we keep track of the current position of the cursor within the buffer. We reset it. We begin processing and parsing that entire frame. In this particular case, we parse the frame. We invoke the IO on the device itself. And then if the device, or if we chose to respond to that IO with some kind of response, we write that directly to the stream, we flush the stream, and we continue. So at a high level, it's just kind of like, continuously pulling bytes from the TCP stream, invoking IOs on the device, returning responses, and then it keeps going and going and going until eventually the client disconnects. So for the frame itself, this check method, basically its job is to verify that we have enough bytes for an applicable frame. So first we need the request magic value. We have flags and an IO type. We have what's called a handle and the offset. We don't actually need these for check. And then we have the length. So for disconnect, flush, and read, there's nothing else here, so we're okay. We are ready to begin processing the frame. But for writes, actually, you need a trailing buffer which contains the entire bytes of the write as well. So if the client tells us that it's trying to write an entire block of data, say 4096 bytes, we actually need 4096 more bytes, or else this will return incomplete. Once we call parse, we already know, for example, that we have a complete frame. So we actually begin unpacking things a little bit. So for example, we look up the type of the IO we're trying to perform, whether it's disconnect, flush, read, or write, or other IOs as well in the future. We grab the handle, and the handle is effectively an opaque reference to a request and response. It's just a U64 or a UINT64, but I choose to treat it as opaque here and actually borrow it from the frame to verify that we're not copying things. So this is where lifetimes come into play. So the lifetime of the cursor is tick A, and the frame has the same lifetime and the handle has the same lifetime. So this frame and this handle have to live at least as long as this cursor does. Once we have the data here, we produce this header, and then depending on the IO primitive here, we match up the IO type UINT16 value with the request we want to perform. So for example, disconnect, flush, and read either have nothing at all or just the header. For writes, we need to actually return a slice into the buffer. So for example, if it says we're going to write 4096 bytes, we slice out that much and return a reference to that. So again, we're borrowing from the buffer with the same lifetime. So the write request actually has a lifetime of tick A as well for the buffer we're reading from. And finally, we return, okay, we got a frame. We have the handle we can associate with it as well. So we actually want to process that. If I go back to the connection, we've parsed a frame. We begin handling the device IO. So we have a frame here that lives for tick A. We are going to return another frame that also lives for tick A. Again, these are sharing the same lifetime. So for example, the handle can be shared between both, and we're able to keep the data kind of like tight and tidy without making copies. If the client returns a disconnect, we have nothing to reply to it. if the client requests either flush, read, or write, we actually perform those operations on the underlying device. So we can either choose to flush the device's buffer, we can choose to read at, which is a combination of seeking to the appropriate location and then performing a read into this temporary buffer, or temporary buffer, or the buffer we allocate within the connection itself, not temporary. We share one buffer for the entire lifetime of the connection, or we can choose to write the buffer to the device directly from the client. This is borrowing a reference directly from the stream buffer, and we're going to write it to the device. So again, no copies, which is pretty cool. Yeah, so once we have that, basically we return whether or not things worked. So for example, the flush operation could fail. We convert it into this error number. If it succeeds, it becomes a 0, which is fine, nothing happened. If it fails, it's possible that either the device doesn't support it. So for example, in the case of a read-only device, we actually return, let's see here. For a read-only device, we can return, for example, not supported. So we convert the result or the error value directly into an error no code. So either none for no error, or not supported, or invalid. Where was I? Once we have all those frames, we can actually choose to write the frame back out. So we've processed the IO, things are complete. For example, we've either written the bytes, read the bytes, or flushed it. We call this write method, and we return, the raw network protocol bytes. So simple reply magic, the error, if it may have occurred, the handle of the operation we're replying to, and we're done, or possibly the buffer in response to the read. So pretty cool. This is a lot of fun. Something I do especially want to talk about though is the device. So this was very, very tricky. The problem I'm running into here is that I wanted to use the type system, for example, to enforce that if a device is read-only, it should always return unsupported operations for writes. Or for example, if we are exposing an SSD over the network and we want to expose trim support, then eventually we would actually add that to this as well. So we have this enum called a device, which has a couple of generic types here, basically. So R is something that can read and seek, and RW is something that can read, write, and seek. So for example, these could be files in memory buffers or whatever else. So the options here for a device, you can either have a device that's read-only, which takes R, or a device that's read-write, which takes RW. For the impl block here, we declare these type parameters RW. The device has RW, again, where it matches these trait boundaries. So R can read and seek, RW can read, write, and seek. If there are any Rust experts here, I hope I'm getting the terminology right. I'm still pretty new to this. This is my first serious generics Rust code. It's been a lot of fun though. So I have abstracted this away in such a way that, for example, if we look at write all at, if we are read only, we return error unsupported. This will get converted to an E inval, and that means, for example, that the client chose to write to a read-only device. So by taking the constructor here in the server type, we take our read, write, and seek, and we choose to constrain the device further, for example, by dropping the write. We are able to use the type system to enforce the fact that we can no longer do writes on this device, which is pretty cool. For things like reads, you end up with a little bit of duplicated code. So for example, here for read, you have this R. R has seek and read. RW also has seek and read. So we just return the length or return early if anything failed here. Flush is the same deal. So if something has the write trait, it also has the flush method available. So flush only works for read write. And then, yeah, these become more simple here. So instead of having to match all these call sites or do lots of logic here, the device type itself, depending on the enum variant, will take care of that for us. So I'm, again, still pretty new to Rust, I feel like, but I'm pretty proud of the way this came out. I think it came out pretty damn good. Yeah, so I think I've given kind of an overview of everything I've learned so far without going too much into detail about some of the nitty-gritty type stuff. You got all these constants here, the code. Let's implement something new. I think would be fun, at least do a little something here. So something I have been thinking about actually is, now that I have flush support, there is actually an option where we can choose to both flush and we can choose to flush either separately by exposing that to the client, or we can choose to flush after use, I believe it's called. So if I go to the docs, one sec, flag FUA, yes. So we can expose a capability to the clients that if the client sends us a flag with its right, which is FUA, what does FUA stand for? Flush under rec FUA, FUA, FUA. What does this stand for? Linux kernel bio with rec FUA. Okay, so the kernel, yeah, hang on here. Forced unit access. So this can be ordered into the read-write flags of a bio submitted from the file system and make sure the IO completion for this request is only signaled after the data has been committed to non-volatile storage. So forced unit access is what FUA stands for. Since we already exposed the flush command, this allows the client, instead of having to send an explicit flush, it can send just this flag with the right IO to make sure that we flush it. So for example, like when we're writing like a file system or something, we want to actually, once we've written the file system out, verify that's synced appropriately. So let's add support for this flag. Why not? nbd command flag FUA. I believe this is part of the transmission flags. So we already have the flush flag. Now we're going to add FUA as well. Forced unit access. So this is part of the handshake. We have a few bit flags. Here we go. So I believe this is the next bit flag actually. So has flags read only, send flush, send FUA. Yep. Send FUA equals nbd flag send FUA. Hey, Lithium, welcome back. Thank you for 6 months of sub. I appreciate that. Good to see you. Nice, he streams again. Yeah. Yep, I'm back. Having fun. So what's cool about... I thought Rust would complain because I haven't matched this on all of the... Oh, maybe not because it's not part of the match statements yet. So we've added the transmission flag now. I'm going to run this cargo watch command, which is similar to the go watch you've all seen me use before. Just to basically watch for changes. So we add the FUA flag. We want to send that by default as well. So whenever we actually send a request to a client, we want to tell them we support this. So transmission flags, send FUA. Okay. And actually, this should make the tests fail, I believe. So let's run the tests instead. They succeeded. Oh, you know what? I think I have a helper now in the tests so that whatever the default flags are, those get added into the tests automatically. So that's fine. Cool. So now we've exposed support for this flag and we send it to the client. So now we need to begin respecting it, actually. So flag send FUA. nbd command flag FUA. Forced unit access. Yeah, so now we are going to add a flag to the transmission phase. So whenever we get a write, for example, this flag is valid for all commands provided the send FUA has been negotiated, which I believe it would. Do we actually have to has been negotiated? Would the client send that as well? Hang on one sec. So when we send flags to the client, I don't know if the client needs to send us that flag back. Flag send FUA. Shoot. Transmission flags. This is the year of Rust. Yeah, Rust is cool, man. It's a lot of fun. It's a different world than Go, but I really do like it a lot. I've been having a ton of fun with it. So no, it appears that the client flags and stuff only include the fixed new style and the no zeros. So the transmission flags are separate. If we go back to my server type, we send the transmission flags to the client. So we have server handshake. Transmission flags are sent as part of one of the responses. let's see here. So transmission flags. Yes. So we send the transmission flags when we send the go export info. So we send the default flags, which are in this case going to be, we have flags, we support flush, we support FUA, which is force unit access, and optionally the export is read only. Okay. So now the client in theory can start sending us requests with that flag attached. So we need to support that in the transmit phase as well. So I actually created a bit flags enum right here, command flags. So the first command flag, bit 0, I believe is FUA, right? nbd command flag FUA. Yep. Bit 0. So CLAN plus Rust is nice. Yeah, I believe it. I've been using VS Code with, I mentioned this a little bit earlier, but I've been using VS Code with the Rust Analyzer plugin, and I really like that. It seems really good. This flag is valid for all commands provided the flag has been negotiated, in which case the server must accept all commands of this bit set, even by ignoring the bit. The client should not set this bit, should not, unless the command has the potential of writing data. Note that existing clients are known to set this bit on other commands, okay? So the client may set this bit on all, no, or some commands as it wishes. And if the server receives a command with it set, it must not send its reply to that command until all write operations, if any, associated with that command have been completed and persisted to non-volatile storage. If the command does not in fact write data, for instance a trim, the server may ignore this bit being set. Okay, so we have to observe this for writes, but otherwise we can choose to ignore it. So is what I'm reading there. So we have flag FUA. How did I name these previously? nbd command flag. No. Okay, so FUA would be the flag name. Unfortunately, Rust does this. Oh no, this is a constant, isn't it? So it can be all caps. Const FUA. I forget the exact bit flag syntax. I'm going to look just a sec here. Const FUA equals right here. The raw value. Okay. nbd command flag. Right. Let's look at our const file. Do I not have the command flags in here? I guess I don't, huh? Transmission flags, transmission error numbers. Let's see here. Transmission, negotiation flags, transmission, command flags, pub const nbd, let's see here, FUA, shoot, is 0, so there'll be other ones as well, so bit 0 is a U16, yes, U16. Of 1 to the 0. Yep. Dredsky, welcome. Thank you for the follow. Appreciate that. Okay. We've added this flag, which is 1 shifted to the 0, bit 0. Yeah. Yeah, that's right. Okay. So it's possible for us to have FUA now. The bit flags macro here will generate the appropriate struct for us. We only choose to observe this. Let's see here. Unwrap or else command flags empty. I previously made it so that we try and read the flag from the bits, but if we don't understand it, then we choose to ignore it, or we choose to return empty, which I guess seems reasonable. But for example, in the case of like a write, we're going to want to return the actual flag. Command flags returned. So now I would imagine the client will start sending us this flag. So we can actually test that. What we could do is just like crash the program or something. We go back to the transmit connection. For the write request now, request flags is not empty. We return invalid. So actually, Have you been working with Rust on the job? No, I have not. So I actually, right now I'm in between jobs. I'm starting a new job on January 25th though, should be good, but it's gonna be doing more Go. That being said, I have been very interested in Rust for like a long time, and I thought it would be fun to take on a big networking project in Rust, and especially doing fast networking. So I picked network block device because it seems like a pretty cool protocol that's been around for a while and does some high speed IO sort of stuff. And it's not as complicated as like iSCSI. So it's been a lot of fun though. So let's run the server, and then we're going to go ahead and try and connect to it with the client here. Connect to it, and then I'll issue a write. And I think that will actually crash the server, or it should hang things a little bit. So mount nbd-0, mount nbd. Can't read the super block. Did I corrupt it? ext4 mount nbd. Device size reported to be 0. Okay. I think this might be the, yeah, okay. Other side returned an error. Error 22. Did you start this project from scratch today? No. I've been working on this for a couple of weeks, mostly off stream, so I'm still fairly new. I guess at this point, maybe I'm like an early intermediate at Rust, I would say. I feel like I've written some decent code now. But I've been working on this for a couple of weeks, but this is my first day looking at it on stream. So returning error 22, which I imagine is actually the code for invalid, right? Einval 22. Yes, actually, yeah, so sweet here. So the kernel is telling us it's receiving einval because the server is rejecting the write because it doesn't support our flag. So perfect. So if we disconnect, I think we just proved that what we're doing works. So the client is now sending that flag. Here, really quick. Let's debug the client flags. Print them to the screen here. And give this another shot. Pull this up again a bit. So connect the device and try and mount it. Yes. So we can see here that for some of the writes, the client sent no flags, but for a few of these now, it's actually sending this force unit excess. So whenever the client sends this point, we need to issue a flush. However, I think that if we're exposing the flush command as well as the FUA flag, I wonder if it chooses to use just this because it's less network IO, I would imagine. But I'm curious now. So debug flush. Okay. One more time. So let's disconnect the devices. Nope. I want to run the server again. We want to connect. So we did get some flushes there. Interesting. So it sent a flush. What happens if we try and mount it now? Actually, I'm going to disconnect the devices first because I think we got hung there for a sec. Why is it using nbd1? I would think 0 would be available, but... new job doing the same kind of stuff. Yeah, it'll be like Go, like control plane type stuff, but kind of just exploring like a new... Sorry, one sec. Is the device... Oh, it's mounted. Oh, let's get rid of that. Mount nbd. Oh, you know what? We've got this mounted in a couple different places. Sudo umount, mount temp. We're going to get really weird results, mount nbd. Okay. Yeah, let's not wedge our file systems here. Yeah, so I'm gonna be joining a new company doing Go as well. But I'm excited about it. It's with some folks I've worked with before, a team that seems to be really smart, cool product. I'm pretty excited about it. So yeah, it'll be really good. So that's gonna be happening in a couple weeks here. No Rust as far as I know, but doing more Go stuff for sure. But I definitely want to keep doing both for years to come. So I'm excited. Again, make sure we got a clean slate here. Let's go ahead and run the server again. We will attach a device. Okay, it sent a flush. And then if we try and mount it, what happens? So sudo mount dev nbd-0 mount nbd. Okay, so we're getting line 87. So the writes have FUA, but the flush does not. Interesting. So it appears to be using both. I wonder what the kernel's logic is here, because I would think that it would make sense just to issue the writes directly, but I don't know. So I think probably what makes sense here is to perhaps pass the command flags directly to this and have this device determine whether or not it supports flushing. So we have the device, we have the offset we're writing at, the buffer for writes. We have the flush command. So we want to trigger a flush after we write. So I suppose we could make a new method for this, because we don't want to flush all the time necessarily. We only want to flush if this flag is set, right? Good coffee. So the header here contains the offset, the flags, and what else does it contain? Sorry, I need to close some windows. I'm trying to think what makes the most sense from an API perspective, right? So we have the flags, the offset, and the length. I think possibly passing the whole header to the write all makes sense. Maybe. So for example here, we pass the request directly to write all at. Request is a header with a lifetime of tick A, right? Header does not have a lifetime anymore. It has the flags, the offset, and the length. Okay, so request offset. Okay. Cargo watch, let's build this, right? So we have to pass header into this scope. Header lives in the frame side of things, I think. You like Rust, but the lifetime stuff is still very confusing. Yeah, it's one of those things you kind of get used to. Like, I mean, honestly, like, I feel like it's helped me write better Go as well, just by understanding, like, you know, you have to correspond to this buffer with this buffer and like whatever else. Like, this has to live as long as this. But really, it's the sort of thing you get better at with practice, for sure. Yeah, so I have to pass. So the header for the device here, we have the crate, the frame, error result. No, we want super frame header as well. So we pass in the header. We borrow the header. We only need to read from it, so we borrow it. We don't want to consume it, right? I guess it might not matter. So the header is no longer used after that point, so I suppose we could just consume it. Oh, no, we can't consume it because we are matching on a reference to self. We're not consuming. Oh, I guess we could consume. No, we cannot consume the header because the header belongs to the frame, and the frame's lifetime, tick A, is tied to the lifetime of the frame we return as well. So we have to borrow a reference to the headers. This becomes read-only, which is fine. And then we check the flags, and if the flags contain the FUA flag, then we know that we have to flush this write. Otherwise, we can choose to ignore it effectively. So, write all at unsupported, write all, and then if the request flags contain transmission flag or command flag, which also is from frame, command flags, if the FUA flag is set, then we have to perform a flush as well. Yep. So that seems correct. So yeah, so again, the type system is helping us here. So this can only be performed on devices which are read-write, which means we have access to seeking, writing, and then flushing. If the client requests that we flush it, we do it. Otherwise, we continue on. Make sense? I suppose what I could do here is this returns a unit. So could I do this and then else, right? Either do nothing or, but this returns an IO result, right? Yeah, so I'd have to wrap it anyway. Okay, so I'll use the question mark operator. Yeah. Let's see here. So must not send its reply until all write operations have been completed or persisted to non-volatile storage. Okay. Client wants us to flush this request, flush the write buffer before replying to its request. Okay. Header, the buffer is the write buffer. Okay. Yep, that's that. This whole operation gets condensed into this one call now. The result of this becomes an error no. So if nothing happened, we return none. Or if, for example, the type does not support writes, we'll return not supported. Or if something else happens, we return invalid. So there we go. Good deal. That should be that. So if I run the tests now, they all pass. Clippy is kind of like your static check sort of thing for Rust. So Clippy here will tell us basically if we're doing something really silly, which is nice. Yep, that looks good to me. I can get rid of the debug line. Let's see here. So we need to choose to ignore. So let's see here. Some clients are known to set this bit on other commands. So let's see here. Let's see here. Ignore flags for now. Some clients may set FUA or similar, although it is only valid for writes. And same thing for reads. So now it would be possible for the client to send a read with the FUA flag attached as well. Ignore flags for now. Some clients may set, yep. So now, yep, we just call read at, but we're actually ignoring the flags for the time being. Okay. So now we support forced unit access. Nice. Good deal, good deal. And this allows the client to flush its request immediately as well. Okay. Let's go ahead and run, let's commit this. Yeah, so transmit frame, support command flags FUA to flush writes. Good deal. First commit of the day, not bad, not bad. Oh, first commit of the stream, actually, not bad. Let's see here. Hang on one sec. Doing pretty good so far. Where are we at? How's everybody doing today? Hope everybody's having a nice, nice Wednesday, nice chill kind of day. Let's see here. Did my GitHub build fail? Oh, no, it did not. Oh, Go proposal review minutes. Okay. Want to take a quick little quick break to review the proposal minutes? Quick little Go break in our day. One sec. I'll pull those up. We've got some Go fans here. Committing off stream. No, I committed on stream. Oh, committing off stream. Yeah, I was doing some work earlier today. Yeah, trying to figure out this. Let's see here. Trying to figure out this whole thing was very hard. Like the different trait bounds and everything. I want to add support for things like trim as well. You know, that'll be just more work, I suppose. But yeah, let's take a look at the Go proposal minutes really quick. Why not? Accepted proposals, none. Cool, good to know. Declined unregistered method to serve mux. Yeah, I'm glad. I feel like manipulating your serve mux like after the fact is really nasty. So you should pretty much create it and it becomes immutable. And I like that way. So I'm glad. Listen and dial for TCP and UDP. It takes an adder port. Oh yeah, we're getting net IP in 118, aren't we? That'll be cool. I'm excited for that. I've actually been meaning to start porting some of my libraries to that as well, but I haven't really been writing Go. So IOFS, I still haven't really played with that. I know that's like the file system abstraction, but we end up with these different, thanks, IOFS. I personally find these interfaces to be confusing. So read dir fs, read dir file, read file fs. Like, I think that perhaps there could have been a different abstraction here that would make more sense or something, because like you kind of end up with like just this base fs interface with all these optional ones. And I feel like it'd be pretty easy for this to turn into type assertion soup. But again, I've actually never really programmed with this. This was added in... let's see here. Go 117. Oh no, IOFS as a package was added in, I don't remember, 116 maybe, 115. Is the expectation that netadder, so as in inetaf netadder, will be updated to use type aliases? I'm actually not sure. That's a good question, because I think that some of the APIs aren't making it over. I don't know. I'm not sure if that's even been discussed, you know? So, netadder, let's see here. Probably worth filing an issue at least to discuss. Let's see here. Netadder, let's see here. API. You only ever use fs sub and HTTP fs. Yeah, that makes sense. I feel like I would probably like use like a restricted subset like that as well. That would probably be the most easy way to kind of keep track of it. But I feel like all the other optional methods and stuff, it gets confusing, you know. Let's see here. Type aliases, huh? Plans for API changes after Go 118 net IP. Let's see here. Brought up a good point today on my Twitch stream. Hi, chat. Otherwise, you might have to wait a few more Go versions to switch it into it in libraries. Will package netadder be updated to use type aliases for net IP? Will package netadder be updated to use type aliases for net IP as of Go 118? Perhaps we use build tags or similar to gate off to ease transition for folks who are stuck on 117 or older. I don't have strong feelings at the moment, but it seems like a good idea to start thinking about at least. I know there is some functionality in this package. What didn't make it into, hang on, so net IP tip.golang.org, sorry, net IP. Where is the docs? Ranges, yeah, so there's ranges, and so ranges and IP sets didn't make it, so such as IP sets and ranges that did not did not make it into the standard lib as of yet. It seems like it would make sense to keep those around here, perhaps backed by type aliases into standard lib. Terran Jokes brought up a good point. Will package.net editor be updated to use type aliases for net IP as of Go 118? Perhaps use build text or similar to ease transition for folks who are stuck on 117 or older. CC all. Yeah. Cool. Good idea, Terran. Good idea. Go ahead and share a link to that. And yeah, cool. Let's go back to the here. Curious. Type parameters, new module for transitional API for tools. I'm sure Dominic will be happy. What's up, Dominic? Hope you're doing well. If you're around, I have no idea. But constraints, rename, KBD. Let's see here. I'm sure some of you who are in the Go community know there have been a lot of interesting proposals as far as things like error handling and such. It's kind of a joke on Go for Slack for a little bit, but all kinds of fun. Multi-dimensional array conversion. I would like that, actually. It's something I was interested in. DTLS. I'm just skimming these pretty much. Yes, crypt, mib-enum. Let's see. This is something that, yeah, would be interesting. So say, for example, here you have a 2x2 float 64. If you want to try and convert that to like a 4 float 64, would be nice without unsafe. I like it, but I have no idea. Let's see here. I'm not going to read the whole thread right now. So Russ's latest comment, you can already do it with unsafe. Alternate avenue for Go4JS would be to improve its implementation of unsafe to make this work. I don't see how it would implement a language change for the same thing if it's problematic to do in Go4JS. Oh, interesting. Unclear language change is needed here. Looking like a likely decline perhaps, but you know, interesting nonetheless. Cool. Nice little Go break there. Let's get back to some Rust. All kinds of fun, huh? Yeah, so cargo Clippy, we are all set. I think the CI build is passing. You know what I should do? I should publish a crate for this. We're at the point now where I should at least get that going. I've got all the metadata and everything set up, MDL, nbd-010, license, yada yada. I just don't have all of the things published yet, I suppose. We could publish a crate though. Maybe that would be interesting. I think kind of what I want to do is I want to publish a crate for this. I want to start writing up a blog post that kind of shares what I've learned so far. And I think I also want to share this with the Rust subreddit. Again, I am not a Rust expert. There might be folks in here who are better than me. And if so, you know, tell me what I'm doing wrong. But certainly I want to make sure that I am doing my best to kind of write idiomatic good Rust instead of like writing, you know, Go Rust or something. So that would be nice, you know. Speaking of, you know, good practices and such, there are actually no tests for the transmit crate yet. I should probably work on that. For the handshake crate, I actually have quite a few tests. So kind of, let's see here. Yeah, I've created like these macros, for example, that given like a frame will, a frame and some arguments will write out the bytes for it. So we have like write tests, read tests, yada yada, all that. We have round tripping tests. So I feel like these are pretty good at the moment. I would like to do something similar for sure. Let's see here. Yeah, round tripping with all kinds of complicated options. Like this request makes no sense, but I guess if you're going to have every possible option in one request, you might as well make sure you can handle it and round trip it successfully. Incomplete. Protocol errors. Yeah. So I want to do something similar for the transmit frames as well. Would be good at least to verify, for example, things like, you know, the request magic, the header, IO types, etc.
The thing is, though, is we also need to implement the functionality for writing these requests out, because in order to test the round trip, for example, you have to have like the client side of things. And of course, if we want our client to actually implement IO as well, we have to be able to write those frames too. So I suppose we could start finishing those. Like you'll see here, I have this to-do macro here, which will panic. So for example, if we try and write IO requests, flush request, read, write, disconnect, these will all return a to-do. Let's start. So we're at the point now where I think my client is capable of negotiating IO, but it just drops the connection. So the server never does anything with it. Like we have a client type, connect. We call go, and then we need to return a client IO connection. So basically we take that connection, hand it over into the transmission raw connection sort of things, and start reading and writing transmission frames. And the first thing I could do probably is to implement a disconnect. So we get to transmit, we send an immediate disconnect, the server shuts it off, and then we're done. That would be a good test, actually. So I think that's something I want to start working on. It is 2:56 p.m. We're going for an hour and a half. I think that'd be a good goal. I'm hoping to go for maybe 3 or 4 hours today. I suppose we'll see. Yeah, so let's write disconnects. So how does disconnect actually look? We receive the frame. There's nothing we do to process it, actually. So the disconnect frame itself, I think, yeah, we basically synthesize this header, which has the flags, offset length, handle, but we don't actually need to return any data here because there's nothing special to handle. So we need to write the request magic, flags, IO type, the handle, offset length, and that's it, because there's no body for a disconnect. It's just whatever lies beyond it. Let's get started doing that. Let's write disconnect frames. So self disconnect. Remove this from here because now it's going to be implemented. So we have to write the request magic. I'm going to go full screen for a little bit because we're going to need multiple things open. So first we write the request magic. So, oops, shoot, the wrong screen, sorry. Write a U32. So request. So what's interesting, actually, at the moment we are just doing the simple version of the IO. I understand there's something called structured requests and replies as well, but the simple version seems to work for my needs at the moment, so I'm just doing that. So we write that. We have then the flags, which is going to be nothing. Write U16, 0, flags, empty. I suppose if I wanted to keep this proper, I could do command flags, none, empty, bits. Seems, sufficient as well. Await, okay, sum. So we return unit, sum, unit, okay. Which means we wrote some data. You don't have to care about the value of it at all. We need to check the error. Command flags. Okay, IO type is going to be a disconnect. So write U16, which is nbd command disconnect. I think I have an enum for that as well, actually. So IO type disconnect. IO type disconnect as U16. Where possible, I like using either the enums or the bit flags or similar. I feel like this is more obvious, perhaps. And I suspect that Rust compiles it to efficient enough code where it probably doesn't really matter. So instead of writing 0, 0 here or whatever, I'll just write this instead. Disconnect, now we have a handle. Yeah, so I guess now we need to start generating our own handles. So thus far, a handle has been basically a slice of 8 bytes, which is opaque. I'm not sure how the client generates them, but the server just responds to whatever the client says. So probably what we want here is I'm guessing like an atomic U64. So if the client is called concurrently, then you can keep issuing IOs with ever incrementing sequence numbers. So I guess similar to what my netlink package does, actually, you start with a random number and you just increment it forever. Would make sense to me. I guess for now, I'm probably going to hard code this, but we're going to need to come up with a handle scheme. So to do md layer, come up with handle generator, handle U64 generator. I guess right has a handle. So we're going to write the handle that we received directly. Right now, this is in response to a client request, but I guess that whatever client type is calling this when it calls write will generate its own handles. So I suppose that that actually doesn't need to be handled here. It becomes the caller's responsibility to generate unique handles. So we write out the handle. Then we have the offset, which is going to be 0. Write U64, 0. Offset length, which are empty for disconnect, I think. So if we go back to let's close a couple of these really quick. nbd command disconnect. So the value of the length of the offset fields in the disconnect must be 0. Cool. Offset length must be 0. And that means there's nothing trailing. So yeah, we have the magic, the flags, the IO type, the handle, which is an opaque slice of 8 bytes. We have the offset, and then we have the length, which is also 0. Yes, that's that. So now we can successfully write a disconnect. We actually have to create a type that can do that now, right? So we need something that can actually generate handles and issue this frame as well. So the way I've been structuring this so far, for example here, I have this device abstraction, first of all, this raw IO connection. So this raw IO connection, this backs the server IO connection, but I'm also going to have a client IO connection that does this as well. So next IO, I might need actually another type here too. So the way this works for this is we have a raw connection type, which is used by both the client and server. This is for the handshake phase, but the same ideas will apply. So the raw connection deals with frames. It can read a frame, it can write a frame, it can parse frames, but it has no concept of like what any of those things are. It just deals with them. And then the higher level types, such as the client, are backed by a raw connection. And the client says handshake, create a raw connection, read and write frames, and then perform higher level ops. So that's effectively what we're going to do here as well. So we're going to start creating a client IO connection or similar that's eventually going to be backed by this lower level raw IO connection. So if we go to the server type here, we can basically copy some of the same ideas. So not quite the same. Client IO connection over S. So an nbd client connection, which is ready to perform data transmission. This is going to be constructed by calling the client's go method. Client's go method. And what we're going to do here is we're going to create this connection and then immediately just send a disconnect, like basically verify we can get to the transmission phase. The server will see the disconnect and just drop it, and that'll be it. So we have go here. This returns a future info, go or info. Okay, so this calls the options. So this actually negotiates options with the server, returns the options we knew about, deals with that, and then once we've called go, the server will proceed into the next phase. So we're actually going to consume the client. So when we call go here, this will actually consume the client type and produce the client IO connection. So once you've called go, you can no longer use the client. So this consumes a mutable reference to self, or does it just consume self in general? I guess it would have to be mutable, wouldn't it? So we return a result, which is the similar to this. Handshake consumes mutable self, returns an optional server IO connection and export. So this returns the export you're linking to, and then the client IO connection over S. Okay, so let export equals, this returns an optional export with an error. Okay, so we have an optional export. So if we didn't get an export, then we can't call go, right? So if we didn't get an export, it means that the export we chose to query was invalid, which I think means we have to return an error because, or I guess we return none, right? If the export is none, we just return none, which means that we tried to go and nothing happened because we didn't actually ask for a valid export. So if export is none, then we just return none. Short circuit. But now if export is some, we continue on. So actually we'll have to unwrap this as well. So let export equals match export. I'm sure there'll be a faster way to write this, like an if let or something, but I'm just going to write out the match to begin with. So none. So if the option returned none, we exit the function, or if it returns some export, we return the export itself. Okay. Yep. We have the export, so we're going to eventually consume the client. I missed the caret there. There's probably like an equivalent map call or something that makes this quicker, but this is fine for now. We are going to consume the connection here. So we're going to return okay, some client IO connection new. And the client IO connection is going to consume self. So the fields of self include the raw connection. And the raw connection contains we need its stream, we need its buffer, and whether or not it's read-only, I guess. Yeah, because what we're going to do is we're going to make it so that if the client connection returns read-only, or if the export says it's read-only, we produce a type that has no access to read to write methods. I think would make sense. But for now, we're gonna ignore that. So we're gonna ignore this field for the time being, but this is something we will get to. Client IO connection. We consume the buff writer and the buffer, so the stream buffer and the stream buffer writer. And then we can eventually begin transmitting or similar. So the client IO connection. And what's interesting, I guess, is I think the client IO connection is going to implement things like the Rust read and write traits so that you can actually use it as a reader writer and it will transparently do the network traffic for you. So that'll be fun. So we need to take over the stream, the buffer, and whether or not the export was read-only. Yep. And we need to return the export as well. Okay. So this transmit function doesn't make sense. So I think what we're going to have is we're going to have a function called disconnect, which just chooses to disconnect from the server. And it actually consumes self because disconnect terminates the connection. So we will actually, let's see here, raw IO connection. It's going to take me a couple tries to get the abstractions right, I feel like, because this is so heavily based on the server type. But I suppose in theory, I'm not sure how much code we can share with this. So maybe this will become the raw server IO connection, because this is all about serving IOs and reading from the buffer and such. So maybe for the time being, I won't create a new type. I'll just continue adding methods in this type. So now we have the buffer, we have the stream, we don't have a device. So we need to be able to read and write frames, right? So we need to read and write transmit frames. And we don't have the capability to do that at the moment because we just have frame parsing, frame writing. Yeah, this is a little trickier because the client is, or the server is managing this device and the client is not. So I think I do have to create a new, kind of a new abstraction here. So we're going to have reading frames and writing frames. So function write a frame, which is going to take some sort of IO frame, which is one of these. Is it in the same file? No, it's in the same module. So handshake frames, handshake raw connection. Is this still in the... Are we in the right module? Yeah, we are. Okay, we're in the IO. Okay. So this is going to produce IO for transmit frames. So we need to get access to use create transmit frame as frame as transmit frame, probably something like that. So given a frame, which is a transmit frame, we want to write it out to the network stream. So this is where we take inspiration from the other package, which is the handshake package. This will produce IO results because we're writing to a network stream. So we try and write the frame, and this is going to be asynchronous as well. Write the frame to mutable self stream. So just need to take mutable reference to self, mutably borrow self, to its own stream, which is the buffered writer. We await it, and then if we sent a frame, we flush it. Otherwise, we do nothing, right? So disconnect is going to send a disconnect frame. So this will return self write frame. This will need to mutably consume self. Write a frame, which is the transmit frame. So transmit frame disconnect, and then wait for it. I think that's it, right? I mean, really quick, let's go build the code. It's been a little bit now. We've been working on this. So yeah, transmit frame, private module. I gotta check my visibility here. So frame type. Okay. So transmit frames are now exposed to the crate. Use transmit frame. Yep. Expected 3 arguments. Oh, that's right. We need the handle, the buffer. Oh boy. Right. So yeah, this gets trickier because we need to generate handles like we were saying. So we need like a handle counter here. For the time being, handle's going to be a U64. Handle starts at 0, sure. Every time we write a frame, we increment the handle. Handle plus equals to 1. And then we let the handle equals a slice of bytes. The handle is an opaque slice of bytes. Shoot. Do we have to allocate every time we write a frame here then? Or can we just like transmute this into a slice of... I guess we could probably... There's probably like some unsafe Rust YOLO, like transmute this into a slice of 8 native NDN bytes, which would be fine. But maybe for the time being, I should not do that, you know? So temporarily, at least we're going to allocate a buffer here. So we're going to make a slice. I guess we can make like a vector. Make a vector, write the bytes into it, and then send it. Just something temporary to make this work, right? So a vector of u8, size 8, we write into the vector. But if we write into the vector, doesn't it also overwrite its data or something? So we're going to write the U64 into the vector. I think this will actually extend the vector though, instead of like, I forget exactly what it is, because like I think if you take a vector as the write trait, it will extend the vector, but if you make like a cursor over it or similar, it will write into the vector, I believe. We're just going to try this for now. So self handle. This is going to be goofy, right? Okay, let's see. I'm going to go ahead and shrink the text here. Sorry, it's hard to read Rust compiler errors. Undeclared module IO. Okay, so let's see here. Use standard IO. Okay. Buff writer, Tokyo IO, buff writer. Yep. Are those compiler errors way too small? Yeah, I'm sorry. It's if I can fix up a couple of them, it'll be better. But return okay none first of all. So okay some, okay none. From frame error is not implemented for standard IO error. Let's see here. Let's go back. So this returns an IO result, but I think we actually, hang on. You can still read them, but I also have you on full screen on a 4K monitor. Yeah, that's the tougher part. So this write function returns the IO result. I think my other one probably should too. I think that was just an oversight actually. Yeah. This should return an IO result instead of a... Okay. Method not found. Oh, does that not return an error? So first of all, the vector has to be mutable because we have to be able to write into it. Write still has to take a handle, which is going to be our slice of bytes, and then a buffer, which is going to be, for now, just an empty buffer for the time being. Let's see here. Bytes mute. Yep, we got to bring that into scope as well. So yeah, you can tell that I'm not as fluent in Rust as I am in Go, right? It's definitely a slower process to write, but I really do enjoy it. I find it to be satisfying to get to work. Let's see here. Sorry. Cargo build. Undeclared module IO. Is that what that said? Transmit frame 174. IO result is undeclared, so we have to bring standard IO into scope. Self cursor. Okay. Boxed struct client. It wanted a boxed error. It found a standard IO error, line 183. Await. And then okay. Let's do that. And expected a reference, found a mutable. So it needs me to slice into the stream. That doesn't make sense. So frame writes to the destination is the second argument. The handle is the first argument. Okay. So could probably fix that a little bit. So we have the handle, the stream itself, and then the buffer, and the buffer is going to be the argument, for example. Getting there. Okay, so transmit frames have a lifetime associated, which in this case is anonymous. We're not using it at all, so that's fine. Method not found. No method expect. Equivalent to... Oh, I have to await it, don't I? Although in this case, I think we want asynchronous. We're using an asynchronous method. It doesn't matter. We're basically just trying to get this working. If I can get like a vector allocated here, and then, well, I suppose what I could do actually is I can make it so that instead of storing handle as a U64, we store it as the slice of bytes, and then we just like manipulate it. But then I have to have like logic to increment within like a byte slice, and it's like meh, not great. We will want a synchronous write synchronous write here, but it's moved. Okay. Oh, it's moved because we're debugging it. Yep. All right, sweet. This compiles. The buffer is never used. Client buffer. It will be. We're going to read frames as well, but we're not there quite yet. So we'll mark that as unused at the moment. If I can actually get this to issue a disconnect, I'll be pretty surprised, right? So we're going to call go. We're going to specify the default export. This is going to give us optionally a tuple of values here. So client go await expect failed to open IO connection. Just going to unpack it because that'll be faster. So now we have the connection and the export, right? So we'll print the export to the screen, and we're going to issue a connection disconnect and just see what happens, right? So does this need to consume it as mutable? Oh, I need to await it. Await. Okay. The client does not need to be mutable. Okay. We have to use the result. I'm trying to print the result is the thing. So that's fine. Okay. Yeah, so in theory here now, we've made it so that our client can connect. It can issue a go request, which will consume the client and actually return a client IO connection. And from here, this type can only be used for IOs. So I'm going to bring the server down here so we can see better. And we're going to run the client, and we are going to see what happens. If I had to guess, this will probably crash and burn, but who knows, right? nbd client. Okay, so transmit protocol request. Yeah, so it looks like we did write this into the buffer, but it extended the buffer, which is what we didn't want. So I'll fix that. That's the thing I was talking about earlier, where the write trait will extend the vector if possible. We'll fix that in just a sec. I'm going to run to the bathroom, get some water, and I'll be right back.
All right, welcome back. Let's see. Oh boy. Streaming is fun, but streaming Rust is mentally tiring. Like, I think I do a pretty good job, but it's tough. So let's see here. All right, back to it. So we have this handle here. This is too long. Just reading Rust is mentally tiring. Yeah, it's I don't know if you're here earlier, Clays, but trying to figure out, where is it? The transmit connection. This. R is read seek, RW is rewrite seek, and all of these trait bounds and stuff everywhere. This took me a while. It took me a while to figure that out and make the compiler happy. But it's pretty cool. I like it. I have a lot of fun with Rust for sure. Does Rust just have like is there just like a method I can use to like transmute like self handle like slice or something? Can I just like slice into this somehow? Let's see here. Swap bytes reverses the byte order. Oh, interesting. Endianness. Hey, big endian bytes. Yes. Nice. That's perfect. So yeah, let's convert this to big endian bytes, I suppose, and then just use that as our handle. That makes sense to me, you know? Let handle equals a slice. And then we borrow the slice, right? So have to slice into it as well. Okay. Yep. Sweet. That's even better. Okay. Yeah, so we talked to the server. It returned the export and we got a disconnect. So I think that we just succeeded. So if we go back here, I'm just going to instrument the server with a couple more debugs. So I understand in Rust there's like different crates you can use for, you know what? I just realized I'm not wearing where'd my hoodie go? I'm kind of cold. I'll be back in just 1 sec. All right, we're back. I guess my girlfriend's watching the stream and she said I'm chilly. Yes, that's true. It's actually pretty cool too. Somebody showed me this. A friend posted. This is from an Etsy store called Refiber Designs. These are like typing gloves, basically. So you put them on your hand like this. Like, you know, I live in Michigan. It's cold. These are pretty good. So, you know, they don't really get in the way, but they keep your hands warm and stuff. So we're gonna do that for a little bit. I'll let me see if I can find that really quick and share, because they're it's a nice little store. Refiber Designs. I'm definitely a fan. Yep, there we go. Shared that link in the chat as well. I'm not affiliated. I just like the product. Anyway, yeah. So we got this working. So I wanted to instrument the server. I think what I was saying is that I know with Rust there are different crates you can use to kind of like do debug logging and such. And right now I've kind of got these debug statements scattered in my code, which of course is not great. So I was planning on getting rid of those, but they are, you know, currently kind of handy. So let's see here. The server, we want to check the IO routines. So the server IO connection. And when we get a disconnect, I want to know about it. So serve, keep serving IOs, handle the IOs. When we get a disconnect, we have no reply. So we write nothing in return. There is no reply to a disconnect message.
The client can then drop its connection, and I believe the server should drop the connection as well. So let's see here, debug client disconnect. Just for a little bit of clarity here. So we got the server running down below. We got a client running up top. Transmit protocol, okay. So the client negotiated go, but then it sent transmit protocol. So something the client said doesn't line up with what the server is expecting. Transmit protocol error of some sort. So let's see here. The one thing is with the question mark operator, much like Go error handling, is that you end up with like kind of these vague errors and you don't know where they came from, and that can be challenging. So the transmit protocol errors are produced either when we're checking frames, so nbd request magic, debug check error, and it can also be produced here. Oh, you know what? IO disconnect, transmit protocol frame type, parse error. I'm guessing it's one of these. I'm guessing it's like the request magic stuff, but we're going to find out really quick as well. So we'll run the server again. We'll run the client again. Check error. So it's failing to check for some reason. Something in the buffer is not lined up properly. It's possible I'm forgetting a field or similar. Let's see. So when we call check, we're checking to see if there are enough bytes in the buffer, and we're not getting the request magic value we expect. So when we write a disconnect, we write request magic. We write the empty flags, IO type disconnect. Let's go full screen here again. Let's close all these and go back. Need to kind of read both sides of the interaction to make sense of this. Okay, so we have request magic. We have the command flags. I'm going to read parse because parse actually decodes all of this. The IO type, and IO type is disconnect, which should have a value of nbd command disconnect. Yes, it does. Reproduce U16. So this is U16 enum. So this will send disconnect as the code. It will send the handle that we chose, which is opaque, so it shouldn't matter. We get the offset, the length. So after handle is 8 bytes, offset length, and then that's it. So we write something. Are we flushing? Are we flushing properly? So we wrote sum. So now the client has to flush the frame. So the client writes something. It writes the frame, disconnect, sum. It returns sum. It flushes the frame. Okay, so we're going to write the frame. We'll show the frame we're going to write. Lunchtime here. Hopefully I make it back before you end, but if I don't, hope you have a great rest of the stream. Hey, thanks so much, Taryn, for hanging out. I really appreciate that, of course. Yeah, it's been a ton of fun. Been going for a little more than 2 hours. It feels like a lot longer. I guess maybe that's Rust for you, but I'll probably keep going for a while. I'm feeling pretty good at this point. But if I get like hungry or worn out, that'll be that, you know. But hey, thanks for hanging out. So we're writing what appears to be transmit frame disconnect. Yep. We're going to write out all the bytes for it. We're going to flush it to the stream, which we consumed from stream is S, a buffered writer over S. You know, I wonder, is it possible where we have anything left in the buffer after we switch to transmit mode? I'm not sure we would, but so this writes the frame and it flushes it, excuse me. Read So in theory, the buffer should be empty. We call go, we get the export, and then we create a client IO connection over the stream, over the buffer. We take our transmit frame here, which in this case is a disconnect. We write it, we increment the handle, put the handle as part of the frame. Let's just go ahead and debug this entire operation, actually, so we can see what arguments we're passing. Is that because we're consuming, hang on, debug, oh wait, there we go. Yeah, so interesting. Okay, let's try one more time. So we got the server running, got the client, transmit protocol. So it returned some is what it's telling us. So we have the handle, the stream, the frame, we're writing. It claims to be writing things just fine, but then we get transmit protocol. Is this not hanging up after a disconnect maybe? Is that why? Because once it hangs up, maybe we want to explicitly close, like drop the connection faster or something. So we write a frame, self disconnect. Oh no, disconnect, yeah. So stream. We can flush the stream, we can shut it down. So shutting down may possibly help. I don't know. Let's see what happens if we shut it down. Because that should make the server stop reading, I would think, too, actually. Because we're consuming self here, we're going to drop it. And then, yeah, I think that would make sense, right? Same deal. For some reason, it doesn't like this. So disconnect is okay. Is it even checking the frame at all? Like, is this? All right, let's this is going to be nasty. Let's print the contents of the cursor. See how many times check is called in the loop here and such. Run the server, run the client. Okay, so the cursor has only read. Oh, okay, so the cursor had nothing. It read more bytes, and then it has 4 more bytes at the end. Are we sending an extra 4 bytes? I wouldn't think so. We're sending all zeros. Or at least the cursor seems to think we are. You know what? I bet that I have some machinery that wasn't consuming the disconnect properly. Like, I probably have to advance past. Let's see here. Disconnect, flush, read, parse. So it doesn't seem like this happens with the other client, though. All right, let's look at the connection really quick. So we set the position to 0, we parse the frame, we advance the buffer as much as we read. So we consume the entire body of the disconnect. Skip handle, skip offset, check length, and then we skip the length. So really quick here. So debug. Show me the header. This is one of those situations where I really wish I could stream on more than one screen, you know, because I've got 3 monitors here and I can't really use them effectively when I'm streaming. But it is what it is. Okay, let's look at the server output. So let's see here. We start a read, it's empty. We consume what appears to be the disconnect request. You can see the 1 in there. So this is our handle. So 1, 2, 3, 4, 5, 6, 7, 8. So that's our handle. And then we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's a frame. Empty header. Flags are empty. Offset 0, length 0. That's the disconnect, right? But then it reads 4 more bytes, and I'm not sure why. So it appears there are 4 more bytes ready. Am I double writing something here? Am I double writing like a U32? If I had to guess. Write a disconnect. Flush it to the stream. Self-stream. Handle. Write the frame. You know what? I'm doing it wrong. Length is not a U64, it's a U32. So if I look at the, hang on. Yep. Yeah, length is a U32. Oops. That explains it. So yeah, our 4 extra bytes were because I was writing 2 64-bit integers, but length is a U32. So that'll fix it. Always make sure you check your integer bit sizes, but I guess it's good to know that my machinery to kind of advance the loop here is working. Yep, so if we send a disconnect, there we go. Client disconnected successfully. So we shut down the connection. The server notices there are no more bytes to read. It drops the connection cleanly, and we're good to go. Hell yeah. Feels good. Feels really good. PogChamp. Yeah, pretty much. Too funny. Cool. Yeah, we're doing good. Sweet. So we can confirm now that we successfully hand over a connection and can do transmit, which is good. I think probably what would make sense up to this point is to verify, write a test to verify the logic we've written so far with the client and such. So let's see here. So first we're going to make a helper for the handle. So function self handle I want to make like a helper function here for the handle that is abstracted away. So helper. If I do this, does that make it inaccessible? That's like the for unused integers. I guess let's find out if that works or not. I'm not sure what the convention is for this in Rust. So this will return the next handle, which is going to be a slice of U8, which lives for as long as the server does. So we're going to have to add a lifetime here, I'm sure. But actually needs to borrow self-mutably because it needs to increment the handle and then return the slice. So this is going to need lifetimes, or is it inferred automatically because it's the same lifetime as the server? So self-handle. But now, yeah, I have to create the handle outside because you can't have 2 mutable borrows at once, right? Okay, so watch. Let's see here. So we have a mutable borrow. Oh, no. Well, shit. So we want to increment the handle, but then we need to borrow the bytes immutably. So I'm not sure this helper is possible, actually, because we have to drop the borrow. Yeah, so for now, I guess I'll leave this inlined. Handle equals handle 0, handle 0. self-handle, bytes. Okay. Yeah, the Rust lifetime rules can sometimes be a little tricky. So for example, in that case, it was complaining because I have to take part of the, this is immutable borrow, and we're mutably borrowing self-stream here. So we're handing out part of the structure, but we're trying to mutably borrow the entire structure here for the handle. So I guess I could make it so that you pass the handle into a function that generates this, but I guess let's see how that, just out of curiosity. Function handle. This is going to be silly, but E64. No, you know, I don't. It's not worth it. It's 2 lines. It's 2 lines. I think only the right frame function is going to need to deal with it anyway, so it should be totally fine. Yeah. Okay. This argument order is kind of bothering me for some reason. I'm going to make it so that the stream goes first and then the handle. It just seems odd. I don't like that the stream is second. I feel like the stream is more important almost. So, and the transmit frame may or may not contain a body, which would be the buffer of bytes we would write as well. So if the frame has bytes, oh no, that's for reads. Shoot. To do MD layer read buffer. So supporting reads is going to be more tricky for sure. The buff equals just says be mutable. Yes. No, immutable. Expected a slice of U8, found a... Oh, I have to modify the other call site as well because I've changed the argument order. So we have the connection type again. This is the wrong connection type. This is the handshake connection again. The transmit connection, have to change the argument order. Yeah, so the stream comes first, and then the handle, and then the device buffer that we're reading into. To do MD layer read buffer. Okay. So for every write, increment the handle counter, and then probably to do MD layer start with a random value or something, you know, so it's just less predictable, I suppose. But so the handle again becomes an opaque series of bytes, which is just big endian in this case because I like big endian better. We shut down. Yeah, so we have the client connection, client IO connection, transmit frame, frame star. Yeah, so the thing is that this crate has these internal modules for handshake and transmit, which are different sort of things, and we're gonna get to the point where the namespaces are kind of polluted by both. So I think probably what I should do is create handshake frame as handshake frame, something like that. Are we exporting the... We are not. Yeah, so... I don't know what all I have to export, or... I guess I'd like to tidy it up a little bit. The problem is, though, is that the handshake in particular has lots of types. And you end up in a situation where there are... Like, for example, all these things like the go request, the frame type, the handshake flags. Like, the handshake crate has lots and lots of types you have to care about. So, but I think I'd like to import the frames specifically. So, frame, like that. Just for clarity. So now anything that takes a frame, I'll call it a handshake frame instead. Because we're going to have both in this file and it will get confusing otherwise, probably. All right, so frame : server handshake, client options, server options, handshake frame. Just for clarity, this will be a transmit frame again. Okay. Go request not found in this scope. The go request comes from that crate. Handshake frame. My search and replace was a little inelegant. Actually, I suppose we can combine these so we can have star and then frame as handshake frame. Probably would be a better syntactical way to do that. So, to do MD layer, try to reduce, try to avoid usage of star. It just gets confusing pretty quickly if you're not careful. Okay, the visibility of that is okay. The visibility of the frame and the frame type. Visible only within the current crate. So the client, handshake frame, handshake frames. Okay, performs a go request to fetch export metadata from the server and initiate data transmission. If a name is none, the server's default export is fetched. If no export matching name can be found, none is returned. So this is going to have similar documentation to the server type that has the equivalent. So right. Let's see here. So if the server is ready for data transmission, some client IO connection export will be returned, so data transmission can begin. Will be returned. Yep, that makes sense. Because the client IO connection is going to be a little more customizable. The server IO basically is just like proxying between a device, but the client IO, I think, we'll have to perform reads and writes on different sorts of things. If name is none, the server's default export is fetched. If no export matching name can be found, none is returned. If the server is ready for data transmission, some client IO connection export will be returned. Yep. I feel like we've written a lot of code. I'm sure Clippy has some stuff to say to us, so let's run that. Just the result. Okay. Let's see here. Disconnect, await, expect, failed to disconnect. IO connection for default export. Okay. Cool. Yeah, so we successfully did it. By the way, my sound quality is great. Not sure what changed since earlier streams. Maybe I've just been listening to a lot of bad quality audio recently. Yeah, nothing has changed on my setup. Let's see. Yeah, same microphone I've had for a little bit. My Audio Technica, my Focusrite interface. I think everything should be the same. On my laptop now, this is not my laptop, but on my laptop I am using Pipewire now, but I have not tried it on the desktop yet. I'd be curious to give that a try. I have no idea if that would change things, but maybe Twitch changed something. Yeah, I guess that's possible too. Cool. So now we have this client IO connection. Does it make sense? Should this be called a client IO connection? Because the server IO connections are called such because there's also a server connection type, which is for a connection to an individual client. So should this be called like client IO or IO client maybe? I guess I'll leave it alone for now. Client's go method creates a connection ready for I/O by consuming the stream and buffer from the handshake phase. Happy New Year. Long time no see. Yeah, long time no see as well. Good to see you. Last time I saw you were writing Go, not Rust. Yeah, I have been working on this project now for a couple of weeks. I've made some pretty serious progress on it, and I'm having a good time. So I figured it would be fun to share on stream. So welcome. Right. So let's see here. Initiates a client disconnect. Initiates a client disconnect from the server and terminates the connection by consuming self. Yep. Does this have to be immutable? Yes, I think it does. Yeah. So when you call disconnect, the client becomes no longer usable because the type system is telling us that it wouldn't make any sense. You know, we've already decided we want to disconnect. So writes a single frame to the server. Writes single frame to the server. Consuming self sounds like auto cannibalism. Yeah. Consuming self as in making it so the type is no longer usable. But yeah. Definitely some things about Rust that I wish, you know, I could bring back to Go. Especially as far as like the type system stuff goes. Like it makes a lot of sense. Like once I learned how things fit together, it's really started to click with me and become very nice. Writes a single transmit frame value to the server. Yep. Okay. So far, we have a client that can now negotiate data transfer and disconnect. Yeah, we will have a generic soon. That is true. I guess in this case, though, like, you know, generics would certainly be useful. I'm looking forward to that as well. But it would be nice, like, I guess the one thing I really miss from Rust is enums. Like, Go interfaces are nice, but having an exhaustive set of enums is so nice. Or being able to, like, choose the mutability or whether or not you want to, like, consume a value is really great, too. If Rust type system came to Go, what would happen to the compilation times? It'd be pretty bad, I'm sure. No ownership yet. Yeah, yeah. Like I said, it's there are things I really appreciate about Rust. It definitely takes more time to get started with, but I have a lot more confidence in my Rust code. It feels like it's all correct, you know. I wanted to update the tests actually too. We can use the disconnect method in the tests, so I want to make sure I do that. I thought my watch was buzzing at me. Actually, I should charge it really quick while I'm here. 2 hours and 39 minutes, going strong. I watch a streamer on a regular basis who is full-time, first of all, and he plays video games, but he streams like 70 hours a week, and I am completely exhausted after like a 4-hour stream, let alone, you know, 12 hours a day, 10 hours a day. That's a long time. So every day, I can't imagine, you know. Meeting time, see you next stream. Yeah, thanks for stopping by. I hope I'll probably be streaming again either tomorrow or possibly Friday. I'd like to keep working on this project for sure while I still have time off. But yeah, thanks for stopping by. Take care. Let's see here. Unknown exports do nothing. Let's see here. Initiate transmission, data transmission with the server. Cool. Yep. So given an export name, which is optional, we request the info for it. We send, for example, we support the fixed new style handshake and no zeros. We want to send a single option, which in this case is go or info. Excuse me. We read from the server and see what sort of options it negotiated with us. And actually, option responses. I suppose we're also going to want to return what we negotiated with the server as well. So for example, if the server tells us to support things like flush, we want to be able to send that information as well. So maybe I should return the server options directly, I suppose, because that would give us more info. Because the handshake frames contain the server options. The vector of known options, the go response. Where are the flags? Am I ignoring them? I think I am, probably. That's an accident. Where do the flags live? From request, option request, the response would contain flags, which would be part of the go response, actually, I believe. So the go response should have info requests in the export. I'm pretty sure the go response should also have our flags. Yeah, so am I not reading those, or am I ignoring those? So the go response should have the info type export should have the transmission flags. So I have my option parser here, which should give us all of that data. Next client option, go. Let's see here. Next server option. Yeah, this code, this is some hairy parsing logic. So we keep the info requests. So we have the flags here, but we're exposing only read-only on the export. We need to actually expose all of the flags now because we don't just support read-only anymore. We also support things like flushing. So the export now needs to expose all of the transmission flags. So flags is a transmission flags. And this actually needs to become public now because we're actually going to expose this as part of the export as well. So it's not just public to the crate. This is now public in general. So have flags, read only, send flush, send. Okay. So I have to fix up a lot of places, I'm sure, because we have things like read only. So client line 81. So we take all of the data about the export, so probably pass all of the flags, I guess, to the client IO connection. So this is going to take all the transmission flags, which is going to contain whether or not the export is read-only, among other things. So let's see here. To do, pick apart and note adjust capabilities such as for read-only exports. So we'll end up returning a client IO connection, probably an enum, similar to what we're doing for devices, where depending on the capabilities we negotiate with the server, we return a different variant. So that will be good. In the meantime, we don't support anything special right now. We just shut down the stream, we write the frame. But now we'll be able to know if we negotiate things like the, like what sort of accesses we support. But okay, let's fix the rest. So handshake frame 392. Probably be faster if I did this all in VS Code, but I guess it's nice to give me a chance to like think too. So we expose the exports flags directly, I suppose. But now the client has to set all the flags that the export supports. So maybe I make it so that the constructor exposes the capabilities or something. The thing is here is that this library supports both clients and servers, but I don't want people to be able to shoot themselves in the foot, although I guess if you are operating at this low level, perhaps you should be prepared to deal with that. So transmission flags has a default method which allocates the flags that we would expect. And you can also attach the read-only flag if you'd like. So I'll make this public as well. Pub is not permitted because it's inclined. Oh, okay. So apparently default is always public. So let's see here. Returns the default transmission flags for an export regardless of client configuration. See, the problem is here is I'm trying to think of things from both the client and server perspective. Like from the client perspective, you want to be able to see all the capabilities the server supports, but from the server perspective, like I don't really want them to be able to misconfigure this like has flags 0. So maybe this is where I make a constructor for the export, I guess, because I don't want to necessarily expose everything. So I'll make this not public necessarily. And when you create an export, I will probably have it attach the flag directly, and then I can add a method on the export. So impl export function read only self bool self flags contains transmission flags read only. Yep. Okay. Let's see here. So handshake frame 398. I want to expose all these flags, but I want to do it in a way that makes sense. So let's see here. So when we are writing a go response, this is coming from the server perspective for this crate, and we want to enforce that we always support all the capabilities, but plus the ability to be read only. So maybe I make it so that you have to construct this using the constructor. I guess this is probably the case for like a builder, right? Like Rust usually likes to use like builders for this sort of thing. So let's see here. New read only. Let's just hypothetically, right? So self, no. New read only would produce a self, but it would take the rest of the fields of the export. I want to carry the flags along with it, but I don't necessarily want to expose the flags. So what happens when you let's fix everything we have so far, and then I'm gonna answer a couple of questions, and then we will continue. So source client line 81. So private. I want to expose the flags, but I want to expose them as like read only. So flags returns the transmission flags, which are immutable. Self flags. Self. Okay. Server 261. Right, so we expose the flags from the export because we need access to them. This method has to be public. And then read only is just a convenience method. Okay. Handshake frame. So server line 261. Export read only. The server IO connection, I guess, also should have all of the capabilities that the client and the server negotiated, I guess. But in this case, the server controls, the server is the one creating the exports. So I guess we'll pass all of the flags for now. Export flags. Transmission flags. Transmission flags. If self flags contains read only. So if the export is read only, then you are forced to use a read only version of the device, which makes sense. Okay, let's fix a few more things. So attempted to take source handshake 901, part of the tests probably. Nope, not quite. Okay. So this is where we actually want to set the flags. Export flags equals the flags that we parse from the Go fragment. Yep. Like so, perhaps. Okay, source bin server. So now if I want to construct a read-only export, how would I do that is the question. So you can't construct this with struct little syntax because the fields are inaccessible. Yep, that's what I was worried about. Okay, so I think we need to make a builder for this, I guess. We probably have defaults here, and then you have to specify, for example, the name and the size, but I guess everything else becomes optional, probably. So, yeah, so what we're going to do, new, so this will be to create an export. This will return a self. So the mandatory fields include a string for the export's name, the size of the export, and I think everything else can be optional. So name, size. The description can, at least for the time being, be empty. Looks like you made it back. Yeah, still going. Trying to probably make a builder here of some sort, but I guess for now I'm just kind of, let's see here. So we're just going to add defaults here, and then we're going to figure it out. So transmission flags, the defaults, because the defaults are that we have flags. We can flush, and we can do sync. So we have flush, we use FUA, and then we can make it so the export is read-only through another. Actually, maybe I'll make it so the export is read-only by default, and then it becomes read-write. Although, function. Oh, so we already have this. We already have this helper. What happens if I get rid of that? Let's just see if we can get rid of it for now, and then source handshake frame, line 408. Let's see here. Oh, so this is where we run into the situation again where, yeah, the export. So we want to write the export flags as they are, actually, because we are now in control of all of them, I believe. So this go response contains an export. We have its size. We have, yeah. So I think we want to write everything as it is. So we write the exports flags directly. Export flags bits. Size flags. Okay. Bin server. Exclamation point keyboard. I use the Kinesis Advantage 2. I've been using it for like 4-ish years now, and I love it. Oof, sorry, my neck's a little stiff. I've been using a Kinesis Advantage 2 for the past 4-ish years, and I love it. I know the Advantage 360 is also coming out fairly soon, which would be pretty cool. Yes, I do believe it does have brown switches. I forget exactly. Yeah, I love my Kinesis so much. So let's see here. Let's mutate itself and produce itself. So self flags set. I like the bit flags, great. Okay, so we set the flag to true. Oh, this becomes immutable, or a reference, doesn't it? Yeah. Because you have to take a mutable ref. Yeah, okay. So name, size, description, block size. We're going to hard code the block size just for now. And then the description will be part of the builder as well, I suppose. So pub function, description, description, string, which returns self as well. Thanks, Taryn. Kinesis Advantage 2. Yep, thank you. I appreciate that. Description equals this. Take it, and then return self. Right? Mutable. Mutable self. Yep. So now we're going to have this export builder of sorts. So the server, we construct export new. We have the name. And then the size is 4 GB bytes. The description becomes this. The block size is already set for us. Found a reference to an export. You know, should I make the builder consume? Do builders typically consume self? I guess they would, wouldn't they? Okay, that works. So it consumes self, but then it returns it again immediately. So that makes sense to me, because otherwise you have to dereference the pointer, which seems weird. So now description is going to be optional eventually. Yeah, that's something I need to get to again. Let's see here. But you can't construct one without the... This API feels kind of weird to me, maybe, because like you can read these fields now, but you can't actually build one with them. Although I guess that's fine. I'm not sure how idiomatic this is, but it seems okay to me. Let's see what Clippy has to say on the matter. Nothing. Okay. If I make the flags public, then the entire thing becomes mutable, which is not what I want. So, let's create a read-only export just as an example. Okay. It's been a while since we've tested this, right? So cargo run. We run the server. The export disk is now read-only. So if we attempt to access it, so we're gonna do this. And then we try and mount it. Dev nbd1 mount nbd. Cannot mount dev nbd1 read only. Why? Sudo dmessage. Write access unavailable. Try mounting with no load. Like so? No load. How does that work? Load. There we go. Yeah. So yeah, it successfully modded the device read-only. Cool. Sweet. That works. And if we remove that, first let's disconnect all the export stuff. So disconnect all the devices. We'll run this again. This export is now read-write. Okay, add dev nbd1. So that's been mounted the entire time, possibly. Disconnect everything. Oh, we forgot we left in the client disconnect. Oops. How long has it been since we committed? Oh shoot, we started doing all kinds of stuff. Oops. That's okay. I have a tendency to do that. Like, I'll start working on one little thing and then I get distracted. Client disconnected. Where's that message coming from? All right, gang. We're coming up on the 3-hour mark. We're doing good. I'm going to go get some more water. I'll be back in just a sec. Yeah, so I just I walked out to the kitchen table. Remember something funny? So I have been working in tech since 2012-ish. Thus far, I have actually never had a MacBook. Work sent me a MacBook Pro, so one of the new ones, the 14-inch 10-core CPU. I think it's the M1 Pro, something like that. The new 14-inch one, 32 gigs of RAM. Yeah, so I officially have my first MacBook for work. So I managed to make it, almost 10 years in tech without one. It's not a framework. I actually do have a framework laptop too. It's my personal one. I love that. Let me go grab that one sec too. I'll get that. as proof. Yeah, so my personal laptop is a framework laptop that runs Linux. Yeah, pretty cool. You know, so it's got the, if you look on the bottom here, you can see the expansion modules and stuff, and you can just pop them in and out. So they're a little hard to, yeah, but pretty cool. So for example, HDMI module pops right in and out. So you can take it and just, let's see here, I'll make sure I do it the right way. Hey, you just slot it in, clicks right in, you're done. You know, so pretty cool. I'm a fan. The framework is great. I'm sure the MacBook will be good too. I've actually never used Mac OS, like no joke. I have used it very little on other people's machines, but I have never owned a MacBook. I have never used one for work, so that'll be new. I'm excited. You know, it is what it is. I'm a Linux guy through and through, but gets Mac, install QEMU, and that Arch, sanity preserved. Yeah. You're waiting for the orange screen frame to come into stock before you order some modules. Yeah, it seems like the framework bezels and stuff are pretty cool. I'm also looking forward eventually to having an Ethernet module. That'll be nice. But yeah, my framework laptop is awesome. I'm actually a huge fan of that. It's very comfortable to type on, surprisingly. So like, I historically have not had a good time. Sorry, a little stiff. I historically have not had a great time with laptop keyboards, but I love my framework. It's very comfortable to use. Very, great for typing, great for coding. Big fan. But yeah, I'm sure the MacBook will be great. It's just funny. I managed to make it this long and never had one, and now I'm stuck. But it is what it is. Where were we? Did we test writes yet? Jonathan Torres, welcome to the stream. Thank you for the follow. I appreciate that. Did we test the read only? We did test read only. Did we test read write? nbd client, localhost, nbd-0, so flags, flush, FUA, mount, nbd-0, mount nbd, oh shoot. Thanks, camera. Yeah, I totally forgot. Oops. Yeah, so all I did was switch back to the code and run the server and try and mount the device. So I can confirm now we've got this and it's read write, which is good. Umount nbd. Okay. And then we disconnect from everything and we're good to go. All right. So yeah, we're at the point now where we have the export, have the description. Let's see here. So to do md layer, probably make this option string, although that was previously a nuisance. No, I can't recall why. Yeah, I played around with this a while ago, but it's been a couple weeks, so I tried to make this an optional string before. It was just a pain in the neck, but oh cool, it's in stock now. The bezel, the blank keycaps, and HDMI expansion. Why do you want, I guess people really like blank keycaps. I don't get it. I feel like it would be really annoying, looking at this, just I'm never going to remember where the airplane mode button is, so it's like, for me, I feel like having the keycaps is important, but I don't use QWERTY. Okay, that makes more sense. Yeah. That makes more sense. The block size will also probably be configurable in this, I suppose. But for now, we don't even support different block sizes. Don't hard code. Force the use of our default flags to prevent weird misconfigurations. Our default flags in this library to prevent weird misconfigurations. Yep. Creates a new export with the given name and a device size and device size. I guess I don't really need to tick these. Yep. Okay. Sets the So that's a human readable description for the export. Marks this export as read only so that clients cannot, as read only so that clients cannot, marks this export as read only when negotiating data transmission. Returns the set of transmission flags applied to this export. Yep. Cool. So I always like to comment everything I write that's new. What's our diff at so far? You know, I've actually been, one of the reasons I went down this rabbit hole is because I wanted to fix the tests up a little bit. I wanted to add like the client disconnect to the tests. We should just verify everything works and then probably go do that. So the constructor is nice. That's cool. The export is read write by default. Creates a new read write export. Let's see here. Call the read only method to produce a read only export. Right. Information about a network block device export. Makes sense. Cool. Let's see here. So going back, look at the diff some more. We added a whole bunch of stuff to the client. So for example, we have, now we pass all of the transmission flags to the server or to the client type. We have the client IO connection, which is new. We wrote on stream today. The client IO connection is an nbd client connection, which is ready to perform data transmission. It's constructed using the client's go method. Yep. Ready for IO, public within the crate, public in general. There we go. So initiates a client disconnect from the server and terminates the connection by consuming self. Terminates the connection. I guess it's implied by the signature that you can't use it anymore. So no real need. Writes a single frame. This is not public because only this type should be able to write frames. We have the handle. We have the frame writes. Okay. I just got a network error from Twitch. Are we still okay? At least my preview of the stream crashed for a sec here, but it appears I'm still streaming. I don't think I'm dropping. Since I've dropped 123 frames over the course of the past 3 hours and 15 minutes, so I think we're okay. If anything's going on or stuff's weird, let me know. Anyway, continuing on. We have this new type. We have reorganized the export a little bit. So we're gonna have to run all the tests to so we always set the flags. You don't see any drop frames here. Yeah, it says I dropped 123 over the course of the entire stream, so I'm not sure how recent that was, but it seems to be okay. We create server IO connection, pass in the flags, read only, makes sense. The handle, we can now write out disconnects. Cool. Yeah, this is looking pretty good. So now what I want to do is I want to look at the test one more time. We probably broke a couple things. Yeah. So handshake frame 1160. Let's see here. Okay. Synthetic export. Yeah. So can I? Because this is within the crate, I can set these? No, I cannot. Okay, so foo.toString description bar toString. I'm gonna have to fix this up slightly because some of the parameters here are different. 256 megabytes. The block size is now going to be 4096, and it's going to be read-only. Yeah, so... Okay. How do we get to... Got some ska in the playlist, apparently. Not really feeling that at the moment. Hang on one sec. Okay. Yeah, so we're going to have to fix up some of the... we're going to fix up some stuff here as well, but... the connection test no longer has read-only either. It's going to be a similar sort of situation where we have an export, we declare, yeah. Read-only is going to turn the radio off. Export new, read-only, right? Got a mismatch parenthesis here, I'm guessing. Yep, there we go. Okay. Handshake frame again. Let's call it all the other tabs. 1789. Yeah, I've got quite a few tests for the handshake stuff. The data transmission has been a little less so. I'll shoot. Yeah, we're going to have to fix up some of these bytes. Unfortunately, that's going to be a slight hassle, but... Why would I not just use the test export here? I'm not sure. Test export. I have to fix a bunch of tests. Yep. Okay, server options go full. Yep. Yeah. So this is where we missed the Go CMP library from Go because these assertions trying to read these byte dumps is not great. Yeah. So let's see. So things that will change. Info, length, transmission flags, name, foo bar. Ugh, yuck. I hate it. I hate it so much already. Yep. We're in a bit of a pickle, aren't we? So manual YOLO comparison by hand. This sucks. Not my favorite thing. I guess maybe I should have tried to save myself some trouble. Sorry. Okay. Probably just a couple bytes of difference, but 03232 169. Trying to figure out where they change. 3 5. It's like the same up until the last row, even. 3002, 30016. So near the end. So the block sizes, right? Okay, that test passes now. So we're going to want to look at the block sizes probably because I made the block size default 4096 now. If I had to guess, block, shoot. Okay, server options, list full. Sorry for the small text. I kind of need it to be able to read what the hell's going on, you know. Probably the same thing, I'm guessing. List full. Block size is going to be 4096 bytes now, right? Okay, that's closer, but we still got something wrong. So foobar, oh, the length value is probably wrong, right? So 0002, 44. Yep, length of 44. Because we added one more byte in the message. Yep, that's correct. Okay, cool. Let's try one more time. One more test to fix the old round trip, huh? Cargo test. Server options. Round trip. This is a big test. 4096 bytes. Got to fix that length of that message again. So 44 bytes in length, 4096 bytes, and then probably the block sizes as well, right? All 16s. Okay, so now it parsed successfully, but the output is unexpected for some reason. So well, shit. Block size, flags are the same. Unexpected frame after round trip. Oh, it's because the export has more info after the round trip. Oh. This doesn't, I don't think this works because, for example, this list export thing doesn't have the same amount of info. So when we convert, we have the size and we just have the size, but the export is the default from the info. Yes, this can't be the test export. We actually have to, hang on a sec. We're going to have to fix this a little bit because info is explicitly requesting less data. So as a result, you don't get things like the export name or its description or its block sizes. You just get the basics. So we have to revert this to what it was. Exports new. So, or export new. Empty name, a size of, I don't remember how large, 256. Something along those lines. But then we also have to remove the, let's see here. Shoot. The transmission flags are going to be the defaults. The size is going to be 256. But then there's not going to be any data about anything else. So, this sucks. This super sucks. All right. I gotta get on GitHub really quick and look up what this was before. Let's see. Shoot. Handshake frame, export. So 256 read only, everything else empty. Okay. So we have to be able to modify the block size. Block size is going to be immutable, self. Let's see here. Is a U32, also return self. Okay, Block size is going to be 0, which doesn't really make sense. But actually, I think it might be some kind of default. I forget exactly what, but. And read only. Did that make it pass? Was that it? Oh, thankfully. Yikes. Big yikes. Okay. We did it. Cargo test. Not sure how good that formatting is, but it's a little better. Okay, so all the tests passed now. That's great. Cargo Clippy. Good deal. To do empty layer. This is not a realistic export. Consider updating. Yeah. Cool. Yeah. So actually, I think we can finally get to the point where we're trying to do what I was like 20 minutes ago, which is to actually fix the connection test. So the connection tests here, these actually do the verification of like the whole kind of like round tripping sort of thing. So we create an export, it's read only. We want to connect to it, and then we want to issue a disconnect immediately after too, right? So instead of calling info, we call go. So this gives us the connection and the export. Could not start data transmission on default export. And then we disconnect as well. So con disconnect. Oh wait, expect failed to disconnect. Server should not have negotiated data transmission. Ah, that's right. That says the info test. The info test is not supposed to negotiate data transmission. You were correct. So, we're going to make a copy of the test. Once it passes, okay. Test go. So test go is going to be the same sort of thing. And I suppose we'll try and figure out how to deduplicate these a bit as well. So the server negotiates I/O, and then it should disconnect as well. So I expect failed to negotiate data transmission. So we get a server I/O connection, and then the export it's for, which I guess we don't particularly care about. And then we actually transmit, right? We have to transmit on something, which is shit. This is where I guess we have like a read-only device of some sort. So like we allocate some memory probably, or like put a cursor over it. Yeah, so the device is going to be an I/O cursor. What do we have imported here? Use standard I/O cursor. So the device is going to be a cursor over a vector of, let's just say, 256 megs. No, we'll say 1 meg in this case. take ownership of the vector. We have this. We immutably borrow. And then we, yes, the device has to be mutable because D has to be read, write, and seek. Returns a value referencing data owned by the current function. Yes, correct. Dot await, expect, failed to transmit data. Hey, it works, I think. So we're negotiating data transmission over this empty cursor. And let's see here. Just want to read only export. In fact, it doesn't even need a name. We could just make that optional too, but could not start data transmission on the default export. Failed to disconnect. We disconnect, we get the export. Yeah, that's it. We don't care which export it picked because we only do the default. We don't do any locking. We negotiate data transmission. We transmit on the device, and then we're done. Yeah. So that's that. Cool. So something that we in the Go community have taken for granted for a long time is the coverage tool, right? So there's a similar sort of thing for cargo called cargo tarpaulin. I guess it's like, you know, the long name for a tarp or something. So pretty funny, but so let's run this and we'll check the coverage of where we're at, and then we will see. I'm just curious to see how much of the, especially the transmission stuff we've covered at this point. Cool. This popped up in the wrong browser like usual. Thanks. Good deal. All right, source. So the server does not have a whole lot covered because we're using the connection stuff directly. Yeah, that makes sense. We are calling into I/O. We're doing read-only I/O. That's cool. Sorry, I should probably zoom this in, huh? Handshake's pretty well covered. Transmit is only slightly covered. So for transmit, we are handling a disconnect I/O like we expect. Create the device. We serve an I/O. Read from the buffer. Check. That's that. So good deal, huh? Cool. Seems like a good amount of progress. I'm pretty happy with that, you know? I guess one thing I'd like to do now is figure out how to deduplicate these tests. I don't understand, I guess perhaps some of the testing patterns as well yet in Rust versus in Go. So I'll have to make some adjustments, but actually something I would like to do, I had intended to use the server type directly, I think, because the server type directly will do the same things. So actually, I suppose this test, first let's stage everything we have so far. But I think that instead of using a TCP listener and accepting a connection on it manually at this point, we probably could use the server and serve a single connection instead. That would allow us to verify kind of the entire logic of like spawning the different tasks and such too. So we will call server bind. So this listener now becomes the server instead. We get the failed to bind server, failed to get server address. And then we should negotiate data transmission over this cursor, I guess. And then the client will tell us whether or not we actually got to that point, so we don't have to verify all this from the server side. So now we call server run, right? Await, expect, failed to run server. So the device is going to be just this cursor again. Okay, so the client comes into here, the client negotiates data transmission, it disconnects, yes, unexpected export, failed to run server, failed to run client, okay. So now I have to remember how to use my own damn APIs. Let's see here. Server bind, use MDL, nbd. Yes. I need the server, and I also need the devices type because the devices type encompasses everything. Yeah. So now instead of creating exports in an arc, we create devices. So devices, new, which takes an export and a function to open it. So it takes the export we just created. And then we have to have a way to open it. So the way I had previously done this, basically we allocate memory and we return a reference to it. I had created like a box of memory and then leaked it, but that of course leaks memory, which is not great, although I think it's the one way I know how to do this right now, so we're probably going to do that anyway. So we have to create a function here which can read from an in-memory device. So we allocate some memory. We try and return the cursor, but yeah, it's going to tell us like the vec doesn't live for long enough and all that goodness. Method not found. Exports clone. Yes, because yeah, it's not going to matter. This is a totally different test. This takes ownership of devices, which is no longer called exports, it's now called devices. We don't really care about the export. We can just print it to the screen, I suppose. I mean, the other one negotiates the actual export, so we just care about being able to connect to it and run I/O. So expected a box, right? Because we have to return a boxed function pointer. So box new, or a boxed closure, yeah. And then the cursor is okay because it's infallible to create a cursor. Did that just work? Really? Huh. I honestly thought it would be harder than that. Okay. So I guess that the cursor lives for long enough. Cool. Yes, we're taking a vector here. We're allocating 1 megabyte of memory, and we use this as our read-write seek with a cursor on top. So yeah, that works. Sweet. Failed to run server. Actually, I don't really need to spawn this as a task. I guess I can just do it in the main even. Server handle equals server run. And then we await the client handle. Yep. So we take the devices, we have the client's ready to go, we have the server's ready to go, and then we run the server future to completion, and then we start the client future and run that to completion as well, and things go as according to plan. Oh shit, now it hung. Never mind. Yeah. Because it can't proceed because the client handle is awaiting. Yeah, okay. I think probably, yeah, we'll spawn both these like this. You can kind of think of this in Go terminology. Like we have a couple of Go routines here, and this is kind of like our wait group. So we'll spawn both of these and we'll wait for both in the main. It seems to be probably the more good way to do it. So this will work fine. No, it does not. Huh. Oh, you know what? I have no way of stopping the server. Do I? Interesting. I know you can pass like a shutdown signal, and there's like a select equivalent for Rust or for Tokyo. That would be a reasonable idea, I suppose. probably makes the most sense, but all right, I guess let's figure out how that works, right? So let's do it together. So Tokyo select. Oh, sorry, I actually want the Tokyo tutorial again because the Tokyo tutorial has an example of exactly this. And basically what we're going to do is we're going to use the completion of the client feature, I think, as a way of stopping this. Cancellation. Tokyo select. Closed. There's something in here about using a Control-C, essentially. That's kind of what I'm looking for. Looping, select, receive. There's something in here. Where's the Control-C? Sorry. I read this like a couple weeks ago. Control select? No. How do you cancel spawn? Spawning maybe? So we keep spawning processes, right? We have individual handles if we want them. Send. Shutdown. Graceful shutdown. Yeah, here we go. Signal Control-C. Shutdown, send, shutdown, receive. So we select on either like reading the next frame or shutting down, I guess would be the way to do it. I don't know if I want to get into this quite right now. I think what I might do for the time being is cheat a little bit and make a helper of some sort that will run and accept a single connection or something. But then that's not quite testing all my logic either. We're close. We're pretty close. So we either block on accepting a new connection or shutting down, I think, would be the way to do it. So the mini Redis crate might even have an example of doing this, but that's okay. All right, so I'm going to commit what I have first. So everything we've staged up so far. I'll push that probably, and I think we're probably going to cut stream. It's been 3 hours and 45 minutes. It's been a long time, but a good time. I've had a lot of fun today. Let's see here. So if my client disconnect. So client, implement, let's see, so start work on transmit phase, add disconnect. Add disconnect method. Cool. All right. Yeah, we're going to call that a stream. It's been a lot of fun, but thank you all for hanging out. I really appreciate that. Let's see if there's anybody. Does my mouse just die? Uh-oh. Oh, I lost it. Okay. Is there anybody we can... Nah. Nope. Doesn't look like it. All right, gang. Yeah, thanks so much for hanging out. It's been a total blast. Hope this has been a lot of fun and very educational, and thank you for hanging out with me. So... all right, take care. Have a nice evening, morning, wherever you are, and I'll see you later. Bye now.